Well, hi, I'm Dan Holohan, and I'm going to teach you about steam in the Dead Men Steam School. And this is going to be a good day because I'm going to talk to you like it's 1900 and we're starting out with a brand new building. And we're going to get into the minds of the people that did this work in the beginning. There's a lot to it, but it's not that complicated. I mean, if I can understand this, anybody can. So let's begin at the beginning. I want to introduce you to the heating load. And that's easy to understand because you've got a building that has no radiation in it, and we have to heat this place on the coldest day of the year, which always makes me smile because the coldest day of the year is the one day of the year when all the radiators are supposed to be hot all the way across. And on days when it's not the coldest day of the year, it's perfectly normal for radiators to be only partly hot. But a lot of that has to do with venting and controls and the quality of the steam and where the steam decides to go. And this is where you come in, because when you're troubleshooting, there's so much that you need to consider. But let's begin with that building as it was made in, say, 1900, and figure out how we're going to put the radiators in and what size they should be. Which brings us to Mr. Mills. Now, John H. Mills was one of the granddaddies of steam heating in America. He was an engineer, not by degree. He was an engineer in kind of the Nikola Tesla or Thomas Edison sense, and that he was just born to this and very brilliant. He worked as a consultant to the H.B. Smith Company, never worked directly for them, but always as a consultant. And he was responsible for a bunch of things. First of all, he wrote a 2-volume book, which you can actually get on Amazon. It's a reproduction of the book, but it's fascinating when he talks about boiler explosions and the way it was in the old days. So he did that. It was considered like the Bible of steam heating in its day. He also came up with the Mills boiler, which they made, H.B. Smith made for many years up until pretty recently. It was a very good boiler for producing good dry steam in a building. I'll tell you more about dry steam as we go on. He gave us the Mills system, which was a system of heating tall buildings with one-pipe steam. See, the challenge there is if you go with a one-pipe riser more than, say, 5 stories, you have this problem of the condensate raining down as the steam is trying to climb up the pipe. And if you go higher than 5 stories, pretty much the steam's going to lose to the condensate that's coming down on it like a waterfall. So John Mills comes up with this idea of, rather than sending the steam up and the condensate down through the same pipe, he says, why don't we begin with an express riser, something that carries all the steam for the whole building, and it's going to go up to the attic space and then circle around from corner to corner and then downfeed the risers from the top to the bottom. So now you have the steam and the condensate traveling in the same direction, and it's feeding those one-pipe steam radiators. And it worked perfectly well because steam doesn't know up from down. It's just looking for a way out. So it's looking for an air vent. And these are the jobs that you go on where you walk into a boiler room and you'll see something like a 12-inch pipe, and it might be a 12-inch screwed pipe. And that always amazed me when I first saw it, because I'd be standing there and I'd be looking at these fittings that somebody put together with wrenches that were, they must have been enormous. In fact, one old timer told me that his grandfather used to work on these jobs, and he said they used to put the fittings together with chain wrenches, and they would bring horses on the job to make up those fittings, if you can imagine that. I was at the top of a building once with a Mills system, and I was looking for the air vent because the building wasn't heating well. And I went into this crawl space with a friend of mine, and we found a T that was at the top of this riser, and it was a 12 by 12 by 3/4 inch T, screwed T, if you can imagine that. And in the 3/4 inch tapping was an air vent that was about the size of a football, a bronze football. And that was what was causing the whole building not to heat well because it was clogged. But I thought about that T and the men who installed that, the people that I call the dead men. And, who were these guys? And, how big were their arms? And what kind of tools did they own? And gosh, it must have been like Popeye and Bluto doing this work. So Mills did that, and we call that the Mills system. Still widely used and still widely seen, not so much used, but you see this in many of the older buildings, particularly in cities like New York. And then Mills gave us what came to be called the Mills rule. It was also called the 220-200 rule. Here you can see 220 and 200. And what this is about is Mills said that for every 2 square feet of glass, we need to have 1 square foot of radiation. And for every 20 square foot of cold surface, which could have been any surface that didn't have heat on the other side, so a cold surface could be a floor, a ceiling, or a wall, we need 1 square foot of radiation for every 20 square foot of cold surface. And then for every 200 cubic feet of volume, we need 1 square foot of radiation. Now that's all great, but I got to back up here a second and talk about this square foot of radiation and what that meant. See, it came first from the first radiator that was invented by James Watt, and that was done in England. I'll show you a picture of his house in a minute. But a square foot was actually a square foot on a metal box, and they figured out that this is a square foot that's going to put out so many BTUs, and here you go. And as time goes by, they get a little bit interested in how we can make radiators smaller and not appear so ponderous on the wall, because the old books and magazines talk about how the women of the house didn't like the way this thing looked. So they begin to make radiators that have a lot of surface area, and it's done with, say, taking brass tubes or copper tubes and wrapping wire around it so you get more surface area. And it's kind of like an early version of what becomes a convector or fin tube radiation, where you got a lot of places where the air can touch the hot surface of the metal. So the challenge then becomes, how do we measure all these ins and outs, all these nooks and crannies, all these convolutions that are made up from the pipes and the wires wrapped around the pipes? And they come up with a brilliant way of doing this, something that I never would have dreamed of if I had the rest of my life to think of it. They figure out that if we take this radiator with all these ins and outs and we dunk it into a big vat of paint, of course sealing the holes in the radiators before you do that, and then draw it out and let all the excess paint drip off the radiator, well, then any paint that's not in the vat is now clinging to the surface of the radiator. So of course this vat is sitting on a scale. They weigh it before they dunk the radiator, and then they weigh it again after the radiator comes out, taking the paint with it. So whatever is missing by weight from the vat, that is the paint that is stuck to the outside surface of the radiator. They then took that much paint by weight and they painted the floor. And however many square feet of surface they could cover on the floor, that became the declared square foot surface of the radiator. Isn't that cool? I wouldn't have thought of that. Would you have thought of that? So keep in mind too that if you're writing this down and you're figuring that this is a great way to do heat loss calculations nowadays, just know that you're probably going to wind up with a boiler that's about 60% bigger than it needs to be for the building, because John Mills is working with buildings that had very little, if any, insulation. These are buildings that are made out of brick and plaster, and considered to the types of windows they had at the turn of the century and in the late 1800s. They weren't windows like we have today. These were different windows. And I often wondered about those windows, and it seemed to me that all of those windows would have been single pane windows with sashes, and that's probably what you think too. Most people do. But then I went and did some more research, and I found out that double windows came before single pane windows. This is an article from the Chicago Evening Post, and the date is July 1911, and they're talking about how now in downtown Chicago, in the apartments, we have these wonderful systems of steam heat. And this is the greatest thing, because now we can get rid of those double windows that the people in the country use, because there's no way to get fresh air into an apartment with the double windows. They don't open. So this is great. We've got a single pane window now. We've got a steam radiator sitting in front of it, and we could be warm and have ventilation through lousy windows. So it was actually the invention of steam heating that did away with the double window. They came first. And this is also why you'll see radiators installed under windows. Because when you think about it, if you've got a room that has a heat loss of, say, 10,000 BTUs, it really doesn't matter where in the room you put that radiator. It could be mounted under the window. It could be mounted on an inside wall. It could even be mounted on the ceiling. In fact, if you've been around enough steam heat, you'll see plenty of radiators that are mounted on the ceiling, and many times in the lower floors, and that's to get them above the boiler water line. So if the heat loss of the room is 10,000 BTUs and the radiator is putting 10,000 BTUs into the room, it really doesn't matter where it is. The reason why it winds up under the window is because they were using these loose windows that allowed fresh air in, and having the radiator right there kind of warmed the air as it was coming through the window. So there's a little bit of history for you. It helps to study history when you're trying to learn about this old stuff. So, 1 square foot of steam EDR, equivalent direct radiation. This is what came along after they stopped painting the floor. And they had to figure out a better way to figure this out. So EDR is the term that we use to measure modern radiators and older steam radiators. And it's based on this. We say 1 square foot of EDR for steam will put out 240 BTUs per hour, British thermal units per hour, but only under these conditions. You have to have 70 degree air on the outside of the radiator and 215 degree steam on the inside of the radiator. Now this is key to understanding steam, this 215 degree steam on the inside of the radiator, because that happens to be steam at about 2 psi pressure. As steam pressure goes up, the temperature goes up with it. And what we're seeing here is that by the very definition of EDR, which the old-timers, the dead men, used to size radiators, they were depending on there being not more than 2 pounds of pressure inside the system, because 1 pound of pressure at the radiator is going to give them that 215 degree steam on the coldest day of the year. So this brings us to a story about how this all came to be, because there was a time in America when boilers were exploding at the rate of 1 every 36 hours. I mean, they were just taken off, and this is because there were very rudimentary relief valves, if any. We were burning coal, we were burning wood. We didn't have an automatic low water cutoff. We can't get a low water cutoff until we have an oil burner. I mean, how would you cut off a coal-fired boiler? You really can't. The best you could do is deny it oxygen. So they had dampers that denied it oxygen based on pressure. But this was a time of rapid invention, and it was a time of tremendous danger from steam boilers. So it was bad for business because contractors are trying to sell boilers for people to put into buildings. Boiler manufacturers are trying to get people to feel comfortable about this new thing called central heating. But the challenge is that people are afraid that they're going to die if they get it. So an organization forms that comes to be called the Carbon Club. And this was a group of the boiler manufacturers, pretty much all the boiler manufacturers in the industry, that banded together in 1898 and 1899. And I have these old magazines that were printed back then that have the minutes of these meetings as they took place. And it was a fascinating thing because the Carbon Club was pretty much brought together for the purpose of making systems safer, sure, but it was also a group of companies that decided that they were going to fix prices, because they wanted to make sure that everybody made a good profit in these days of central heating when it was brand new. So they were in defiance of the Sherman Antitrust Act at the time, which was law and had been law for almost 10 years. But the government was going after people like Rockefeller. They weren't really looking at the boiler people. So the boiler people were just flouting the law and doing what they wanted. So they began to get concerned about the safety issue in a big way in 1899. And they held a meeting in Manhattan at the Murray Hill Hotel, which was on Park Avenue. It's no longer there. But on December 18th and December 19th, they had this meeting, and they decided in that meeting that from now on, all steam boilers should be run at 2 psi. All hot water boilers should be run at 180 degrees. That's why we do it, because they decided at that meeting that the difference between steam equivalent direct radiation and hot water direct radiation should be a factor of 0.6, which is why steam boilers put out 240 BTUs per hour, and hot water boilers with an average water temperature of 170 degrees Fahrenheit only put out 150 BTUs. They also decided at this meeting over 2 days that there should be something called a pickup factor, which accounts in a steam system for the pipes that have to be heated up before we can heat the radiators. The same thing went for hot water. So these people in 2 days pretty much changed the face of heating as we know it. And that was done on December 18th, December 19th, in 1899. So when we enter the 20th century, we're entering at a time when the industry declares that there is not a building built from this day forward that can't be heated with 2 pounds of pressure or less. And this is why buildings such as the Empire State Building runs on 2 pounds of pressure. So that makes you kind of wonder why the troubleshooting job that you're doing in Mrs. McGillicuddy's 3-bedroom house is running at 8 pounds of pressure, doesn't it? We'll talk more about this as we go on, but trust me on this, it is not the pressure that is heating the building, it is the latent heat that's in the steam. The way the Carbon Club did this in 1899 was they established a chart that said if you've got a certain load of steam moving through a certain size of pipe, you ought to do it this way. And if you do it this way, the pressure drop of the steam as it moves from the boiler to the radiation will be about 1 ounce of pressure loss for every 100 feet of travel. So if we start out with 2 pounds of pressure at the boiler, 1,600 feet down the line, or 160 stories straight up in the air on the coldest day of the year, we will still have 1 pound of pressure left over, and that satisfies EDR. So that's the story behind that, and that's the reason why if you see a pressure troll, you better crank the pressure down, because that may be why the building's not heating. Your pressure is just too high. Crank the pressure up too high, your air vents will stop working. If the air can't get out, the steam can't get up, and we'll talk more about that as we go on. So, the radiation, what are we going to put in this building? Let's take a look at some radiators and talk about the beauty of these things. Now there's James Watt's house, which was the first house in the world to get a radiator. He had a greenhouse attached to the side of his house, and he decided to bring a pipe indoors, and the greenhouse didn't have radiation. It just had a steam pipe that went right in and sent steam into the air, which humidified the plants and also warmed the air. But he didn't want his books in his library to get all steamy and wet, so he brought in a radiator, which he made, which was 2 flat pieces of metal kind of held together, and that's where the term EDR comes, square foot of radiation comes from. EDR follows, but this is the first house to get steam. The British tried steam for a little bit and then realized that they would prefer hot water because it was safer, so they abandoned steam, and steam comes to America, and pretty much this is where all the research is done, and this is where it gets born. Here's your first commercially successful radiator. This was done by Stephen Gould in 1854, and this is called a mattress radiator. This is actually in a house in a town in upstate New York, and this is called a mattress radiator because it looks like a mattress. It's very thin. It's only about 1/4 of an inch thick, and it's 2 plates of metal that are being held together by a rolled edge. There's a piece of rope on the edge. And there's the old radiator with Mrs. Cassiope, who is no longer with us. She's touching that radiator valve, which is beautiful. October 3rd, 1854. So this house, by the way, is still being heated with these radiators. So this is perhaps the oldest steam system in America. Stephen Gould wanted the women to like it, so he made it decorative. He made it kind of look like wood, and nevertheless they hated it, so it didn't last long in terms of production, but it's still out there. And if you ever want to see one in real life, go into Manhattan and find the Fish Bar, which is down in the East Village of Manhattan. Go in there and have a drink and a shot, and you will see a mattress radiator up there, which have been in service since before the Civil War. So what are you installing today that's going to be around in, say, 150 years or so? Isn't that amazing? How wonderful this old stuff can be. So here's your 2 types of radiator. This is a column radiator, which is a true steam radiator. And I say that because the inlet for the steam is at the bottom. This is a 1-pipe steam radiator. The steam is going to go in the bottom, and the condensate is going to come out the bottom through the same pipe. The nipples that connect one section to the next, these are the sections like the slice in a loaf of bread, are on the bottom of the radiator. There's no connection between sections on the top. They get away with this because steam is lighter than air. So when it enters a radiator, it displaces the air like helium displaces air. The steam is going to go to the top of the radiator and displace the air downward. The air is going to move from section to section to section and be vented out of an air vent that's somewhere around the middle of this radiator over here in the last section. So these are called sections. These are called tubes over here on the side. 1, 2, 3 tube. That's a 3-tube radiator. This is a thin tube radiator, which was used for both steam and hot water. And here you can see that the inlet is at the bottom or at the top because they use these on 2-pipe steam as well as 1-pipe steam. And now we've got nipples connected completely across the top and completely across the bottom. So if we were doing this with 2-pipe steam, the advantage there is a 2-pipe steam inlet valve can be partially closed. Over here with the tube type radiator, the inlet valve has to be fully open or fully closed. If we try to throttle it, you're going to get water hammer inside the radiator and the squirting air vents because the steam and the condensate have to share that same valve. So it's got to be completely open or completely closed. It's most all of the time left completely open, summer and winter, and people regulate the temperature by opening the windows. So be careful too if you're troubleshooting one of these, because since the valve is forever open, it's likely that the internal parts of that valve will fall apart, just rot out. So the seat might fall apart, and drop down into the pipe. So if the radiator is not heating, it pays to pop the bonnet on the valve to see whether the valve is still intact. Over here on the thin tube, if we sent the steam in the bottom, it would rise because it's lighter than air and go to the top, and it would then move across the top sections, and we now have to have the air vent somewhere down around the bottom or the middle of the radiator over here, because if we put the air vent at the top of the radiator, the steam would come in the bottom, go up the first section, rise, move across horizontally, and shut the air vent before most of the radiator is hot. So that's why on this type of a radiator, you always see the air vent installed down here at the middle of the last section. If they brought the steam into the top of the radiator, the steam would, of course, go completely across the top, and that was often done with two-pipe steam. So we would have, say, the steam coming in the top and the condensate coming out the bottom, typically on the opposite side. There would be a steam trap or some kind of a vapor device at that point. The advantage of doing two-pipe this way is because when the steam comes in the top, it's going to condense in the radiator, and the condensate is going to dribble down the inside of the sections, and it's going to give you a nicer feeling to that radiator, because when we make water into steam, we have to add an enormous amount of latent heat to get the steam to change state, even though it's still at 212 degrees. So with two-pipe steam and this thin tube type of radiator, we're taking advantage by feeding it into the top of not just the latent heat of the steam, but also the latent heat of the condensate as it dribbles down. So this sort of a radiator gave you more of a nice radiant glow. When you stood next to it, it was more even heat. It just felt better than the column radiator. So the wealthier people in the early days of central heating often went for this type of a system, and at the turn of the century, what we called vapor heating. I'll explain more about that in part 2 of this seminar. So when we're replacing a steam boiler, what we have to do is measure the radiation, because with steam, the boiler's ability to produce steam has to match the system's ability to condense steam. This is because steam is a gas that desperately wants to turn into a liquid, and when it hits cold metal, it's going to condense and stop moving. It's no longer steam, now it's hot water. So the way we measure a hot water boiler is to do a heat loss on the building and then to provide a boiler that can take care of the heat loss on the coldest day. With steam, you can go ahead and do a heat loss if you want, but you also have to consider the amount of radiation that's in the building, because if there are a lot of radiators, we're going to condense a lot of steam. So if you put in a boiler that's too small, the steam will condense on the radiators it can get to, and some of the building will remain cold. If you put in a boiler that's too big, it's going to short cycle and send steam at high velocity up into the building, and that can cause you other problems. So you pretty much have to hit it pretty close to what's in the building. So it pays to go measure the radiators, and in the case of this column radiator, we'd be looking at a steam chart for radiation that shows a 3-column radiator, and we count the number of sections. So let's do that. So this is that 3-column radiator, and we count 1, 2, 3, 4, 5, 6, 7, 8, 9 sections, and then we measure from where the foot is to the top of the radiator. So let's say it's a 3-column radiator. It has 9 sections, and each section is 38 inches high. We got that by measuring from here to there. I'm just arbitrarily picking a size. And that means that each section will put out 5 square feet of equivalent direct radiation. So 9 times 5, 9 sections times 5 square feet per section is 45 square feet. And 1 square foot of radiation puts out 240 BTUs. So 45 times 240 gives us 10,800 BTUs per hour. So we write that down, and then we go measure the next radiator and the next radiator and the next radiator. And once you get a total radiation of the building, and you add a suitable pickup factor, which we'll talk about in a bit, and that gives you the size of the boiler that you need. That's the proper way to size a replacement boiler. Don't go by what's there. It might not be the right boiler. It might be the reason why the boiler's failed. Don't go by, that's called the label method. I mean, of just going. I once had a contractor tell me when the boiler didn't heat the building, I said, how did you size the boiler? And he says, I brought in the biggest boiler that would fit through the door. That's called the doorway method of sizing. Don't do that. It's not a good way to do it. Do it the right way and you'll be a professional. So this is a column radiator that's not connected across the top, and this was converted to hot water, and you can see that it's very difficult to get the air out of a radiator like this. So they take this beautiful Victorian radiator and they drill and tap each section to let the air out. And isn't that just horrible? What you do to something that's that beautiful, and look, it's going to leak anyway. So don't do that. If you have this type of radiator, don't try to convert it to hot water. Keep it as steam or change the radiation. Speaking of beautiful old radiators, this is a Bundy radiator, which was one of the very first. And what we're looking at here is a 2-pipe air vent system. So this is the supply pipe over here, and on the other side, this is the return pipe. Now I know that because the air vent is over here. This is an air vent that was made by a man named Moses Breckenridge, and it was called the Breck in honor of him. And he did work for the H.B. Smith Company, and he was related to Stephen Gould, the guy that invented that mattress radiator. So many of these people in the old days were related to each other, either through business or through marriage, or actually related to each other as family. So the 2-pipe air vent system was a way of having a large radiator that would operate with an air vent like a 1-pipe system, but it would avoid having to drain the condensate out of the same pipe that's supplying the steam. So the radiator is pitched in this direction, and we are letting the condensate drain out a separate pipe. So it's a 2-pipe air vent system. We'll look at this more as we go along, but you'll know it by the fact that the 1 pipe on the supply side is always going to be 1 size larger than the return side. So if this were 1.25 inches, the return side would be 1 inch. That's how you'll know it. And the Bundy radiator had a top that was just decorative. It lifted off, and each one of these tubes that went up and came down was pushed into, it was pushed into the bottom. We just skipped up to Reed radiator there. It's pushed into the bottom, so there's no connections across the top, and the top is just decorative metal. So around that same era, we have the Reed radiator, which worked in a similar way. Each one of these pipes is capped at the top and pushed down into the iron base, and there's a baffle that runs up the center of the tube. So when steam enters through the bottom base, it goes up one side of the tube on one side of the baffle, and the air gets pushed down on the other side. The top, again, is just decorative. The hot air would just rise up through the section, and I'll show you photographs of this in a moment. This is one of my favorite radiators. This is in Washington, D.C. This was the old post office, which was bought by Donald Trump and turned into a luxury hotel. But the day I visited there, I was there with my wife and my daughters, and they wanted to go to the gift shop, and I wanted to look at this radiator because this is, these were all over the place. This was fascinating to me because I'm looking at the way this thing's put together. Here, there's no nipples on the top, nipples only across the bottom. We've got 2 sections. One, the steam goes into here. Steam also goes over to here. And we've got these nipples that are angled. Could you do this? Could you put this together? There's not a union anywhere in this thing. And it had been converted to hot water. We could see here the hot water pipes. And I don't know when that happened, but probably years ago. And then my daughters again wanted to go to the gift shop, but I said, no, wait. We have here the remnants of what was called a Paul system. Andrew Paul was the man that invented vacuum heating. And this device took the place of an air vent, and it had a little thermostatic element inside of it. So this threaded connection here at the bottom would be attached to a metal pipe that would go down into the basement. And a building like this, like the old post office, would have had a steam engine in the basement. The steam engine was there to run a generator to provide electricity. And back in the day, they would use the waste steam coming off the steam engine. They would run it through an oil separator, and they would send the waste steam up into the building to heat the radiators. And then down by the steam engine, they would use an ejector, which is a specialized T that has a reducing cone along the run. And if you shoot steam through that run of the T, it's going to go through that diminishing hole of the cone and pick up velocity. And when it does that, Bernoulli's principle kicks in, Bernoulli's law. And it's going to have an effect on the bull side of the T, the side of the T. It's going to create a suction. So that's the same principle that makes an airplane fly. We have rapidly moving air that's going to lower the pressure under the wing, and it lifts the plane up into the air. So here we're going to have rapidly moving steam going through an ejector that's going to cause a vacuum, and the vacuum is going to suck all the air through these Paul air vents and pull it down And the result was they would save up to 30% on the fuel bill because they would have the air removed very quickly out of the system, and then the steam would travel at speeds up to 60 or 70 miles an hour to go from the boiler or from the steam engine up into the radiators. So I was fascinated by the remnants of this being in a building that is still standing today and now is a luxury hotel. My guess is Mr. Trump probably removed these, but I've got to get over there and take a look. So here, okay, this is a Reed radiator. And here's the inlet valve. And here you see this pipe. This is the remnants of that old Paul system right here. And when we look at the top of this radiator, before we do that, this was the fitting, not the Paul fitting, but this was what was in those radiators that we just looked at. And this radiator, by the way, is in the Dakota apartment building, which is the apartment building that's on Central Park West and 72nd Street. And that is the building where John Lennon lived and died. It's an iconic New York City building built in 1884. It still operates on the same system that was installed in 1884. And I show you this because this was from the Dakota building. And if you remove this back piece here, it's just a little screwed cap, what you find inside here is a cork. And the cork was designed, because this went where the air vent would normally be, the cork was designed to swell when steam reached it. So we're here connected to the steam engine that definitely was in the basement of the Dakota because they produce electricity and steam and also sold their excess electricity and steam to neighboring buildings as they were built. So the Dakota actually became a cogeneration plant in the early days of heating. So this was called a Pemberton fitting based on the manufacture of that. So here we have the top removed on that radiator that we just looked at. You can see the remnants of the Paul line here. They've since gotten rid of those valves and they're using air vents. And since we removed the decorative cap, you can see on the Reed radiator, this is just capped and there's a baffle that goes up on the inside of each one of these individual tubes. There's the radiator in a service part of the Dakota from 1884. This is the remnants of the Paul line. It's a two-pipe air vent system now. This is the supply, this is the return, and here we've got an air vent. What's interesting about this building is there are people that work there whose job is to open and close these radiator valves when the tenants get either too hot or too cold. So, I like to think of them as two-legged zone valves because you got crazy rich people living in this building and famous people living in this building, and we're still dealing with a heating system that was installed in 1884. There's the Dakota. And I love this picture because my brother and I grew up in Manhattan, just on the other side of the lake from the other side of Central Park from where the Dakota is. And when we were kids, my father would bring us over here and we would slide around on this ice. And this picture was from the early days, and I love it because everybody in this picture has something in common. If you look very closely, you'll notice they're all having a nice time. They have that in common. And if you consider a little bit more, you'll also realize that every one of them is dead. So that's the beauty of steam heat. The people come and go, but the buildings remain. And the heating system that was warming that building on that day is the same heating system that's warming it today. I love this picture because in front here we've got Central Park, and there's very few trees here. But the people on the skating rink that day, they never realized that there was going to come a point in time when we would have something called rock and roll, or a band called the Beatles, and then a Beatle named John Lennon was going to be assassinated right over here on this side of the building, and that his widow, Yoko Ono, would designate a part of the park called Strawberry Fields. And back when this picture was taken, all those trees were just saplings. So it's nice because the people come and go, but the building remains. And years go by, and you can see here, this was Christo when he went into Central Park, and he put up what was called the Gates. It's a wonderful art project. So that on this cold winter day, that building was still being heated with that same system that the skaters looked at in 1884. Point being, there are so many buildings like this in the world that are landmarks that have these old systems in it. And if you're the person that can figure out how it works, and it's not that complicated, you will become a very valuable person, because it's what's in your head makes the difference. You could work with your hands, but what's in your head? Do you understand what you're looking at with these? Oh, and look at the romance here. Here's an old radiator that was designed for a pantry, and you could put your turkey in there and warm your plates. Try sticking your turkey up into a duck. See what it tastes like after you go at it. And people go into old buildings and they rip out radiators like this and they trash them. And I just think that's comical, because then you'll see the radiator show up on eBay and something like this would sell for, say, $5,000. So when you're throwing these things out, just keep in mind what you're putting in the dumpster. One of my favorite systems here. It's called Indirect because the radiators are not in the room. The radiators are suspended like boiler sections inside of ductwork down below. And look at this. We're bringing in 100% cold air, and it's wafting up through this hole over the metal and coming out through a decorative grill into the room. Sometimes these grills are in the floor. This was the favorite system of the wealthy people because they didn't want to have the radiators appear in the room. You'd see the radiators in the servants' sections, but not in the main areas where the rich people lived. And they were also afraid of the air because after the Civil War, we had a problem in America with disease, and people didn't fully understand. People didn't understand at all, pretty much, until Louis Pasteur shows up and figures out that there are things called germs. But prior to that, they thought it was something in the air that was making us sick, and they thought it was vapors coming off of people when people were crowded into a space. And again, this is a time with teeming immigration and crowded cities and poor ventilation. So they thought it was the vapors, what they call vitiated air. People would breathe out poisons from their bodies, and the poisons would accumulate in the room. So the wealthy people that could afford central heating wanted lots of fresh air. So they would bring in this cold air from the outside, and it would just come up into the room. And there's no return air duct in this building. The return air duct is actually the single pane windows. So the warm air would come into the building, and it would just leak out through the bad windows and into the outside. So the windows were your return air duct. So as you can imagine, this was pretty expensive to operate. And oftentimes in these old mansions that have this heating system, in the interest of saving fuel, they will close up these outside air inlets and try to make it work just like that. But at the same time, they're upgrading the windows and they're sealing up the cracks. And you find out then you've got a heating system that won't heat the air, because unless the air can move out, the hot air can't move in. So in a case like that, we often have to use the basement stairs as the return air duct work by just replacing the basement door with a louvered door. And now you can have air move from upstairs back downstairs. And we've got to cut some grates into the side of this air inlet here, this main cold air supply duct, to get it to work. Here it is in real life. You can see this one is one pipe steam, and it's not working well. There's a lot of rust here from the leaking air vent. But when you're replacing a boiler, you've got to look at this and try to figure out what's in there, because you got to get a reading and a rating on what's in here. And if you can get it open, that's what you're going to see. And there's a good rule of thumb here with this, that if this pipe here, this is a 1-inch return going back, the supply would be bigger. But we look at, if it's 1.25 inch pipe going into it, there's going to be 80 square feet of EDR, probably not more than that inside that box. 1.5 inches, which you don't normally see bigger than that on these, it's up to 100 square foot of EDR. So that'll give you a good sense of what you're dealing with. If you have further questions on these, you could always go to heatinghelp.com and go into the section that has the Heating Museum, and it's going to give you a lot of these old ratings. The old books are in there, and you've got access to it. So there you go. Just go into the Heating Museum, go into the Systems Help Center, and you're going to find a lot of these ratings in there. For instance, here's old steam. And if you look here, you can see that there are PDFs of catalogs, and all this is free for your use. And some of these catalogs go back to, 1897 and even beyond. And if you're looking for old radiators, say you're trying to get a rating on it, you could look over here, and you might see something like this in there. So here's a Verona radiator. There are ratings in there for all these old things. If it's a question about something that's old and weird, you're probably going to find your answer on heatinghelp.com. And it brings me to this little event, which took place during the winter of 1918 and 1919. It was called the Spanish Influenza. And after the Spanish Influenza came and went, The Board of Health nationwide declared that people have to keep their bedroom windows open to let in fresh air to prevent influenza, pneumonia, tuberculosis. And people went beyond that. They kept not only the bedroom windows open, they kept the windows open in the whole house. And I noticed this in doing research for the book that I wrote called The Lost Art of Steam Heating, because in the books that were written in the 1920s, they began to refer to the fresh air movement. And they said in these books that now that we have the fresh air movement, we have to design the heating systems for the coldest day of the year when the wind is blowing and also when the windows are open. So they actually began to size boilers and radiation for open window ventilation. And I didn't understand what that was about because they didn't explain the why. They just kept referring to the fresh air movement. So none of this is in the heating textbooks, but I did some research into social history and American history, and I learned about the Spanish influenza, which they never taught me in school. And what was fascinating about this is the worst disaster in the history of mankind. This thing came and went, and it didn't start in Spain. It started in Kansas, in an army base called Camp Funston. And we were involved in the Great War back then. Spain was neutral in the Great War. And because they were neutral, they were able to point out that many people were dying worldwide from this disease. In America, we didn't want to talk about this because in talking about it, we would have given aid and comfort to the enemy. The Axis powers felt the same way. They didn't want to talk about it. So nobody wanted to talk about it. But once it came out that there is this flu that is deadly, and it's spread by breathing, it's spread by coughing, it's airborne, people would be up in the morning and they'd be well, and they'd get on a streetcar and they would be found dead at the end of the run. They killed you that quickly. And it was terrible because it went after mostly younger people. And it was so deadly that it killed, the estimate is 50 million people in that one winter. Now that is more than died in every war we've ever had. That 50 million people represents the entire northeast of America. And this all happened in one winter. And it happened because of Spanish influenza. After that, the virus mutated and it never came back. But if it ever came back again, there is still no cure for this. But it had a dramatic effect on central heating, particularly because of when it happened. This was 1918, 1919. It happens at a period when people are finally beginning to accept and want central heating. So it affects the size of the boilers and the size of the pipes. And we find out now that we've got oversized radiators that are putting out so much heat. So the people say, please do something. And they ask the government to get involved. And the government does research because we're now involved in the Great Recession. And the radiators are too big and we're trying to save fuel. So the government finds out that if we use a certain type of paint called a bronzing, an aluminum bronze or a gold bronze paint, this is paint that has metallic flakes in it. And if you put that on a radiator as the last coat, it will cut down on the radiator's output by 20%. You see aluminum bronze right here. So a radiator that's bare, not painted at all, puts out 240 BTUs per hour. If you paint it with this aluminum bronze paint, the output drops to 192 BTUs per hour. And it's only the last coat that matters. If you paint it above, on top of that, say if you painted it black, it would go back to being 240 BTUs. If you painted it terracotta, which is the color of a flower pot, it would actually pick up 3.8%. You'd have more output. So the color of a radiator does indeed matter. And this, by the way, is why radiators are painted silver. So if you see a radiator and you're walking around with a client in the building and the radiator is silver, you could tell them the story about the Spanish influenza and why the radiator is that color and how this was done by the government to cut down on the output so people wouldn't be as comfortable. They will think you're fascinating because you will be fascinating because when you know stuff that other people don't know, everybody's going to want to hang out with you. That's why radiators are silver. And if you go to the Heating Museum on heatinghelp.com and look in old hot water, old steam, and under radiators, look for does the color of a radiator matter? And this is going to give you the 1935 word for word National Bureau of Standards report that explains the science behind that and how this bronzing paint works and why some radiators are painted only on the front or only on the back, or some in some rooms painted, some in other rooms not painted. It lays the whole thing out for you, and now you know why they are the color that they are. But that still wasn't enough to cut down on the oversized radiators. So they began to recommend that we put enclosures over radiators. This was not done to keep the children from being burned. Believe me on that. I'm 66 years old. I grew up with steam heat, and I touched the radiator, but I only touched it once because I was not a stupid child. But if you look at this, this is actually to cut down on the radiator's output because the radiator is oversized as a result of the Spanish influenza. So if we do something as simple as put a shelf over the top of a radiator, that stops the convective air from moving in. It bumps into the shelf. And it says here that you would have to add 20% to the size of the radiator to get the same output that you would have if that cover were not there, that shelf were not there. Over here, we've got no change because the center of the enclosure is solid. There's holes at the bottom. There's holes at the top. So the cooler air can come in here, get heated, and move right through. This one over here, it actually says deduct 10%. So this is going to give you more output because we're creating kind of a chimney effect here. We put a board in front of the radiator, an enclosure. We've got a hole in the bottom, nothing in the top. So we create a chimney effect. More air moves across. It's kind of like adding a fan to the radiator, going from, say, a fan coiled unit with the fan off compared to the output that you get if the fan comes on. This one over here is my favorite because this is the enclosure that you see on most building radiators. The top is solid. The front is perforated with 1,000,000 holes. And it says here, add 30%. So this says if you put that enclosure on a radiator, you're going to have to add 30% to the size of the radiator to get the same output that you would have if that enclosure were not there. People that sell these radiators nowadays, these radiator enclosures nowadays, talk about how this improves the efficiency of the radiator. Well, it does if the radiator is oversized. I mean, it's got to cut down 30% of the heat that you have in the room. So that's why it appears to improve the efficiency. So painted silver cuts 20%. Use this sort of enclosure, cuts an additional 30%. That's how they dealt with the radiators that were oversized as a result of the Spanish influenza. And notice while we're on this slide too, that every radiator is placed 2 inches away from the wall. That was always the ideal spacing. If you're ever moving a radiator, keep that in mind. It's supposed to be 2 inches away from the wall. And again, it's to create that chimney effect of the air moving behind it. Okay, so we figured out the heat load of the building. We figured out how big the boiler has to be. We figured out the radiators and where they're going to be. And now let's look at a few ways of controlling them. Pneumatics. This is a radiator in New York City, in the New York City Public Library, and I liked it because it had pneumatic control over here, which pneumatics means air-based, and over here we have a steam trap. So let's look at that first. Steam traps trap steam. It's an aptly named device. That's the beauty part of most of heating. If you want to know what the thing does, you just turn its name around and it tells you its function. Air vents vent air. Steam traps trap steam. Condensate pumps pump condensate. And if you want to extend that to plumbing, you could say that P-traps, well, you know. So we've got here a normally open automatic valve. And the way it works is inside the cover here, we've got a bellows that's partially filled with a volatile liquid. Typically, it's alcohol. And we pick a liquid that boils at a temperature lower than water. So alcohol will boil at about 180 degrees. And we put this in here, and the bellows is partially filled with the alcohol, brought up to temperature, and then sealed while the alcohol is boiling. And then they remove the heat and allow the bellows to cool. So now the alcohol is going to condense inside, and the atmospheric pressure of the air on the outside of the bellows is going to cause the bellows to scrunch up. At the bottom of the bellows, there's some sort of a pin that goes into a seat. So this is normally open, and steam pushes the air through the radiator trap because before a radiator trap can trap steam, it must vent air. It's going to push air downstream where it'll leave the system through either an automatic air vent or the vent line on a condensate pump or a boiler feed pump receiver. So when steam arrives at 215 degrees, it's going to cause the alcohol on the inside of the bellows to flash into a vapor. That's going to increase the pressure on the inside of the bellows, which will cause the bellows to expand, pushing the pin down into the seat, and the trap is now closed. At that point, we need to have about a 10 to 15 degree drop in temperature across that trap before the trap will reopen. So with a thermostatic radiator trap like this, it is possible to check to see whether the trap is working during the winter by taking the temperature here on the inlet side and here on the outlet side. You should always see at least a 10-degree difference in temperature between those 2 points. If you're not seeing that, there's a good chance that the trap has failed and it needs to be replaced. On the supply side, we have a pneumatic valve. Pneumatic means air, again. So here, this is the valve body. It's a normally open, spring-loaded valve. And on top of it is a bellows that's charged with air pressure. This line comes from a compressor. And what's neat about pneumatics, it's very like steampunky and old school because the thermostats actually have compressed air running through them as well. So when you touch a thermostat, because the room is too cool, you're going to hear a hiss of air being released. And the air pressure that's pushing this bellows down to push the stem into the valve will be released, and the spring-loaded valve, which is normally open, will open, and steam will enter the radiator, and you'll have heat in the room. The room gets warm, the thermostat senses that. It sends a signal to the compressor, and the compressor comes on, and it goes chugga, 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 and you get air coming in here to push the stem down. So this is very mechanical and pneumatic, and there's a lot of stuff that can go wrong with it. So if you have got a pipe that gets damaged or if the system begins to leak, that's going to be a problem. So Allen Bradley was the company that produced most of these, and these are all pictures that were posted on heatinghelp.com by the people that come to the wall, which is our bulletin board, and here you see the profusion of pipes, a lot of copper pipes, a lot of steel pipes going out throughout the whole building, lots of places where things can go wrong. And when they do go wrong, this usually gets abandoned, the pneumatic system. You can see the remnants of it here. And in this case, it gets replaced with a thermostatic radiator valve. And this is a non-electric valve. This one's made by Dan Holohan. It's a normally open spring-loaded valve. And on the top of it snaps this temperature-sensitive head. Now, it's not sensing the steam, it's sensing the temperature of the air in the room. So as the air warms up, this is very sensitive. And the stuff on the inside, it could be a liquid or it could be a wax, will expand and push down on the normally open spring-loaded valve to lessen the amount of steam that goes into the radiator. The top of the knob is marked 1, 2, 3, 4, 5. That's the European approach to this. And over here you can see it's obviously on 5 right now. This is equal to 50, 60, 70, 80, and 90 degrees Fahrenheit. Now this job was having a problem because when the pipe got hot, the heat from the pipe was coming right up into the bottom and causing the valve to close. That's why they got it set on 5, because the radiator valve was shut on the temperature of the heat in the pipe. So the way this was fixed was we exchanged this self-contained head for a remote sensing head that could sense the temperature somewhere else. Put it over here on the wall where it's not going to feel the temperature of the very hot pipe. Easy fix. This is a one-pipe steam radiator. It's got an air vent on it. Two-pipe steam radiators, unless it's a two-pipe air vent system, don't have air vents on them. They have steam traps or some kind of a vapor device. But here, we've got an air vent on here. So the steam is coming in, condensing, the condensate is rolling out to the valve, which has to be fully opened or fully closed. If it's fully closed, the radiator is off. If it's fully open, the radiator is on. There's no way to throttle this and make it work, because as soon as you start the throttle, the water won't be able to get out, so you'll start to get steam banging the water into this section, and it's going to squirt it out of the air vent, and the radiator will just fill up with water, and you'll have problems. So to do a thermostatic radiator valve on a one-pipe steam radiator, we can't use it here as we did on the previous slide. But what we can do is put it between the air vent and the radiator to deny the radiator's ability to remove air, because steam and air have different densities, and if the air can't get out, the steam can't get in. So we're going to use this sort of a thermostatic radiator valve. So this over here would go into the radiator where the air vent would normally be. This is an air vent over here, and we like to use a straight shank air vent on here so the condensate can more easily drip out. This is a normally open spring-loaded valve, and onto this screws this temperature-sensitive head. So this is going to sense the temperature in the room. We have it set for 3, which would be 70 degrees Fahrenheit. So when the room gets to be 70 degrees Fahrenheit, it's going to shut the radiator, TRV, thermostatic radiator valve, and that means that the radiator can no longer have access to pushing the air out of the vent. Now what's critical to make this work is we've got a built-in vacuum breaker here on the bottom. That's important because once this closes, the steam inside the radiator will begin to condense. And when it condenses, it shrinks tremendously. The difference in expansion from water to steam is 1,700 to 1. So when you turn, say, a pint of water into steam, you're making 1,700 times the volume of steam, the gas, that you had in the 1 pint glass. So you would need 1,700 empty pint glasses to collect the steam that's going to come off that 1 pint of water. Now, when it turns back into water, it does just the opposite. So 1,700 pints of steam volume will shrink back down into 1 pint of water. So the steam system begins to operate like a bellows. It always begins completely filled with air. Every steam system starts out completely filled with air. When steam forms, it goes off like popcorn. It just expands out of the boiler, pushing the air ahead of itself because steam is lighter than air, so they will not mix together. Steam will push the air ahead of itself down a pipe like it's a plunger going down a pipe. And the air will look for an air vent on the way out. But when the steam condenses, it shrinks and the air will come right back into the building through the air vents. Now, if we've got the air vents sealed by the thermostatic radiator valve, because we don't want the room to get any hotter, the vacuum that's going to form inside the radiator due to the condensing steam will draw more more steam into the radiator. So we need a vacuum breaker on the bottom. So as soon as steam begins to condense in the radiator, the vacuum breaker senses that drop in pressure and lets air back into the radiator, and that's the way you keep a radiator from overheating. And then in real life, here we've got a remote sensor. The problem on this job was, the temperatures were all wrong. Well, the temperatures were all wrong because they put the remote sensor right on top of the steam radiator. Not too bright, but that's what people will sometimes do. This was in a law office in Manhattan. Here we had the remote just dangling in space here rather than mounting it on the wall. So somebody got paid for this without finishing the job. But there's the vacuum breaker right there. Good example. Okay, so we've got the radiators in. We know what size they should be. We know where they should be, and how to size the boiler. So let's take a look at the way the boilers are rated. When you look at a boiler manufacturer's catalog, you're going to see 3 things that they give you in terms of ratings. One is called input, and that's the actual heat that comes out of the flame. So the input is the value of the natural gas or the fuel oil. Back in the days of coal, it was harder to figure because the coal varied by where it came from, the type of coal, the size of the coal, the quality of the coal. But with propane and natural gas and fuel oil, it's pretty straightforward. So that's the actual heat that's coming out of the flame. Some of that's going to be lost up the chimney and through the boiler jacket. So what's left over, it used to be called the gross rating, but then the Department of Energy stepped in and took over the name. So they now call it the Department of Energy heating capacity. And this is the stuff that's left over to go out to the building after we've taken the losses through the chimney and through the boiler jacket. So when you look at a boiler manufacturer's rating and it gives you an efficiency rating, say it's 80%, that means that 20% of the heat is lost up the chimney and through the jacket. And it's a questionable thing whether the heat that's lost through the jacket is actually lost to the building, because chances are the boiler is inside the building. So there's some controversy there. But this is what's available to go out to the system. So that's the actual load of steam that now has to heat not only the radiators, but the pipes between the boilers and the radiators. So it has to take this massive amount of steel and bring it from ambient temperature up to 215 degrees, and that's going to require energy. So the pipes are going to cause steam to condense. That's why we insulate pipes, so the condensing is limited, because we want the steam at the radiator, not in the pipes that are inside the walls or down in the basement. So by the time we get out to the radiators, what's left over, what didn't die on the way to the radiators, is called the net rating, and this is the actual rating that's going to be there for the radiators. So when you measure the radiators in the building, trying to figure out what size boiler you need, you're coming up with the net rating. Now, to this, manufacturers have traditionally added what's called a pickup factor. So they take net times a factor of 1.33, and when you add that together, that gives you this, the DOE heating capacity. So net plus 1.33 is a DOE heating capacity. What to keep in mind, though, is that in the early days of steam heating, the heating capacity for both steam and hot water systems was figured at 1.56. So it was a lot bigger than what we have these days. This all changed after World War II. They lowered it to 1.33 for both steam and hot water. And then in 1967, they further lowered the pickup factor for hot water to 1.15, where it stands today. And they kept it the same for steam at 1.33. But it makes me wonder, if I'm working in a building that was built in, say, 1890 or 1900, and it has the original steam radiators and steam piping, is this 1.33 pickup factor sufficient to heat that building, since it's built into the boiler manufacturer's catalog? So that's a question to ask. And it gets worse if they've removed asbestos insulation and they're not replacing it with fiberglass, because then the heat load of the pipe actually increases by 5 times. So you have a lot more pipe to heat up to temperature, and often a boiler that you use to replace the boiler that's there may not be big enough, even though it's the same size. So then too, what happens if you're on the job and you notice that radiators have been removed? Notice the radiators are no longer there, so in your radiator survey, for purposes of sizing the replacement steam boiler, you can't measure a radiator that's not there. But the piping that served that radiator is still there. So the pickup factor should be larger than 1.33. When I see missing radiators like this, what I'll do is figure the actual radiation that I'm measuring and substitute the manufacturer's built-in 1.33 pickup factor with my own, which would be 1.5. And then I would select the boiler not from the net column, but from the Department of Energy heating capacity column. And that usually is enough to make up the difference. So let's talk about the near boiler piping now. And this is critical, because back in the day when they made steam boilers, they made them specifically for steam systems, not for hot water systems. And the difference was the steam boiler had a very large outlet to allow the steam to leave the boiler at speeds no greater than 15 feet per second. That was the standard back then. And the goal is, if you're under 15 feet per second, the water's not going to leave with the steam. It's not going to get sucked out of the boiler by the high velocity steam. A steam boiler also had a big steam disengaging space, what we call a steam chest, where the steam could rise off the surface of the water and have this kind of a cavern to play around with before it left through that really big hole. And the steam boiler also had very wide sections internally, so that the steam bubbles that were formed down where the fire is could rise up through the section without creating a lot of turmoil on the surface. So after the OPEC oil embargo in the 1970s, we began to see hot water boilers being used on steam systems with just the changing of the trim. So now suddenly we had boilers that sure operated at higher efficiency because they contained less metal and less water, but they were also subject to higher velocity steam because the exit holes were smaller, the steam chest was diminished, and the sections were much more narrow internally. So we started to see a lot more surging and priming of water, which is water getting sucked out of the boiler. So the boiler manufacturers, since they couldn't do it in their manufacturing facility because they had to meet the government standards for efficiency, they began to tell the installers that you now have to follow proper near boiler piping techniques to remove the water from the boiler, from the steam, before it gets out into the building. So the water is definitely going to get sucked out of the boiler by the steam, but we've got to catch it in the near boiler piping and put it back into the boiler before it gets out. So let's look at a practically perfect drawing. This is from the New York City Housing Authority, which is loaded with steam heating systems. And I've been looking at this drawing probably for 30 years, and it's practically perfect. And what I like about it is we can go step by step and show all the elements of good near boiler piping. First, notice that we're taking 2 risers to the header. Now the header is this pipe that's horizontal, that's going to carry all the steam. And note that it's offset through 2 screwed elbows. The reason why we use screwed black iron pipe here is because that header is going to expand at a different rate than that boiler. And unless we've got something to play with where these elbows can turn a little bit, that header will put incredible force down on these pipes and which will act like a crowbar to actually rip the boiler sections apart, and the boiler will begin to leak. So we offset here, and this is why I hate to see copper fittings being used on near boiler piping, because the soldered fitting definitely will loosen up as time goes by and come apart. I've seen too many of them. Now this is the takeoff that goes off to the system, and notice it's made between the last riser coming up off the boiler and this pipe, which we call a header drip and an equalizer, which is going to take any carryover water and put it back into the boiler. We never take any connection to the steam system between the risers that go up to the header, because we want everything going in the same direction. Steam and any carryover water comes out of here, goes that way, goes that way. If we were to have this connected here, the steam would be going this way with the carryover water, this one would be going that way with the carryover water, and we'd wind up with a big glob of water here that would get thrown out into the system. The boiler would then go off on low water, we'd have water hammer around the building, and lots of problems. So, one of the rules I like to follow is that you should always have a minimum of 2 feet of space, vertical space, between the top of the boiler and the bottom of the header. Now, some manufacturers say 2 feet of space between the water line and the bottom, but I don't think that's enough, and I'm going to prove it to you in a minute. So 2 feet of space there. Now over here, we've got the piping that's going to take the steam up into the building. It's good to have a full-size T here, because if you reduce the pipe right at that T, Bernoulli's law is going to kick in. The same thing that made those ejectors work on those steam engines that we talked about earlier. So if you've got a sudden reduction in pipe size, the velocity of steam will pick up and you'll suck water out into the building with the steam. So we want to reduce it a point above that. Carryover water gets thrown back into the boiler, into this pipe, which is called an equalizer. Now, this is an equalizer because you've got steam pressure inside the boiler that's pushing down on the steam water line, the boiler water line, trying to shove the water out of the boiler. Now, the equalizer's job is to put a force back here to shove that water that's trying to escape back in. So it's kind of like having a scale with the same amount of weight on both sides of the scale. This is also why it's good to keep the amount of fittings in the equalizer to a minimum so you don't have excessive pressure drop through there, and never to put valves or anything like that in here. So just a turn and a drop down, keep it big so that there's less pressure drop through there, and that's why we've got this equalizer there. Back in the day, they would put a check valve here in the return to stop the water from backing out of the boiler, but they found that the check valve would often fill up with goop, and the goop would cause the check valve to stay open and the boiler would lose its water. And during the time of coal-fired boilers, we have no low water cutoffs yet. So that's a dangerous thing. So that's where the equalizer came to be. On the return piping, over here, you see it comes up into the equalizer, several inches below the boiler water line. This position is set by the boiler manufacturer to get it above the crown sheet, which is where the fire is, and in a safe position. And this came to be known as the Hartford Loop, because the Hartford Steam Boiler Insurance and Inspection Company, which is one of the few companies in the world that would actually insure steam boilers at a time when they were blowing up every day and a half, they began to mandate this at the beginning of the 20th century, because they, before that, the return water came back into the bottom of the boiler, and if a return line should break, all the water would leave the boiler, and suddenly you had the potential for a boiler explosion. So they said, let's bring it back into here, very close to the boiler water line, so should a return line break, the water can only drain to this point. It's kind of like siphoning the water out of a swimming pool. If this were your siphon hose, when you got to that point with your water line, it would stop draining the pool. So it bought them the advantage of having time to notice that there was something wrong. So that's called the Underwriter's Loop or the Hartford Loop in this day, and it's still being used today, and it's still a great idea, because even though we have a low water cutoff, there's a chance that this might fail or get plugged. So the Hartford Loop can save lives, and it did over the years. At the top and at the bottom, we've got 2 valves, and I think these are essential to any steam boiler. This is a return valve, and this is called a king valve, like it's wearing a crown. And it's not anything special. It could be a gate valve or not a glow valve, but a gate valve or a butterfly valve. That's called a king valve because it's the main valve for the whole system. And what that allows us to do is once a year to close these 2 valves and to be able to blow all the mud out of the boiler. And for that we use ideally a full-size valve here, a ball valve, which you take the handle off of it once you install it so that nobody bumps into it by accident, because the steam system is open to the atmosphere, and the steam is constantly causing the iron and the steel to corrode, and all that corrosion washes down by gravity and winds up in the bottom of the boiler in what's called appropriately the mud leg of the boiler. So this is mud that's made of metal, and it's very, very thick, and it will not just drain out by gravity. So if you tried to just open the mud lake valve without having any steam pressure in the boiler, the weight of this water, which is not much because a column of water 28 inches high only exerts 1 pound of pressure. So from here to the mud lake, maybe you've got 2 pounds of water weight. So 2 pounds of water weight is not going to move this mud out of the boiler. And that drastically cuts down on the life of the boiler because the mud prevents the water from circulating properly, and you wind up with sections that get too hot and they begin to break. So by using a king valve and a return valve, once a year we can go back, close these two valves, isolating the boiler from the system, build up about 10 pounds of pressure in the boiler, and then open the mud valve. And when you do that, all that crap's going to get blown right out of the boiler. So if you're selling boilers to customers, it pays to talk about these valves because it adds a little bit of price to the installation. Actually disappears in the price of the installation, but it's going to dramatically increase the life of the boiler by having them there. So in your customer self-interest, definitely talk about that. And while you're at it, talk about this additional valve down here, because we could work with the return valve and this drain valve over here to waste the condensate, because when we put in a new steam boiler, it begins to act like a scouring pad on the old system, and all that crap that's up in the system is going to work its way back. And why put all that crap back into the boiler when we can catch it with the return valve and drain it out of here for a few days? So these valves here really make a big difference on a replacement steam boiler. Over here we have, because this is an apartment building, we have to use two pressure trolls. One is the operating pressure troll. Now the steam system typically operates, say, between 1/2 psi, that's the cut-in setting, and 2 psi on the high side. And this is wired in series with the thermostat. So whatever controls the, let's get some heat signal to the building, whether it's a heat timing device or whether it's a thermostat in a room, that sends a signal which starts the burner off. The burner is going to fire until we reach whatever pressure we set the pressure troll to. And as I said, the Empire State Building only needs 2 pounds. So your building, if it's smaller than the Empire State Building, probably needs a lot less than 2 pounds of pressure. So we set that at the minimum. And on the standard pressure troll, that minimum would be, say, a 1 pound differential. So if we're cutting in at a 1/2 pound, which is the lowest setting you can have, the boiler will cycle between 1/2 pound and 1.5 psi. So as long as the thermostat's calling, the boiler will cycle between those 2 points. It's called the cut-in setting, which is typically a 1/2 pound, and the cut-out setting, which would be 1.5 pounds. Now, when the thermostat gets satisfied, the burner just shuts off, and everything just cycles back down to 0. So that's the way the pressure troll works. Now, the reason why we've got a backup pressure troll here is this one would be set to, say, 10 psi, and it's only set to cut off the burner, and it has a manual reset button on it. Now, the purpose of that is because it's an apartment building, and people who live in apartment buildings are more valuable than people who live in single-family homes, because the code requires that we have 2 pressure trolls watching out for them. In case one of the pressure trolls fails, we need the backup pressure troll to shut off the burner if we ever get to 10 psi. Because if we get to 15 psi, that relief valve is going to pop. And a relief valve on a steam boiler is not like a relief valve on a hot water boiler. Hot water boiler relief valve is kind of friendly. You know, it sputters, it spits a little bit and then stops. A steam relief valve is Jack in the Box. And it's a scary, evil Jack in the Box, because when that opens, it is sized and designed to dump that entire boiler load instantaneously into that boiler room. Now, I say that to you because if you work on these steam boilers, one thing I want you to always do is keep the boiler room door open. Because if you're in a boiler room with the closed door, when that relief valve pops, the temperature in that room is going to go from whatever it was to 250 degrees instantaneously, and all the air in that room is going to be displaced by that high pressure steam coming out at 15 psi. And that will kill you instantly. So don't be in that room if that relief valve pops with the doors closed. So one complaint here is, you notice on the bottom here, they've got what's called a pigtail, and we're looking at it from the side, so you really can't see it. But a pigtail would be, look down in the front like a pig's tail. It's curved like that. And its purpose is to fill up with water and keep the latent heat of the steam from reaching through to the control. So it extends the life of the control dramatically over the years. The reason why you see it positioned this way with the donut hole on the side is because back in the day when we used mercury type switches in these, if we had the hole looking at us like we were looking at the donut right now, when the pipe heated and expanded, this control would actually tip left and right, which would mess up the mercury and screw up the settings. So they moved it this way so that when the control goes, it moves toward you and back away from you, front to back, rather than side to side, which doesn't affect the mercury switches. But notice that this pigtail probably will clog up, because they almost always do. And when it does, it's going to take offline both the operating pressure control and its backup. So this is not a good place to save money on pigtails. If you've got 2 pressure controls and a gauge, they should be on 3 separate pigtails. Down here we've got clearly this is a McDonnell-Miller automatic water feeder and low water cutoff, and its job is to maintain a minimum water line. So it's set up on these quick hookup fittings off the gauge glass to feed at a minimum amount of water level, and that's to replace water that gets lost by minor leaks and evaporation, because steam systems are open to the atmosphere, so there's always going to be evaporation. So that's not designed to maintain the center of the gauge glass or 2/3 of the gauge glass. When we start out on a steam boiler, we begin at a level that's about 2/3 full, because think about it, the water that's between the 2/3 and the 1/3 is out in the building as steam, heating the radiators. When it comes back, we want it to have a place to go inside the boiler. So if a feeder were to feed at the 2/3 point, when the water came back from the system as condensate, it would flood the boiler. So the automatic feeder is set at a minimum level, not at the operating level. And this, according to the manufacturer, needs to be blown down every single week, because it will fill up with mud. And if it's not blown down every single week, it's going to cause the feeder to fail, and it's going to cause the low water cutoff to fail, and that's going to create a problem, and that could burn down the whole building. Now, this is an insurance picture that was sent to me by the people at McDonnell & Miller. This is the float that's supposed to operate the automatic water feeder and the electrical cutoff to the burner. This is what screws into the bottom here. So this was what was never blown down. You could see that the blow-off valve was never open, because this is the mud, and this is the consistency of this stuff, and this is sitting under the float, so the float just sits in it like it's sitting on the ground. So the water level went down, the burner kept firing because there was nothing to shut it off. The boiler began to glow cherry red. It heated the pipes. The pipes got hotter and hotter. They came in contact with wood, and they set the building on fire. The insurance company came. People said, we've got insurance on the boiler. Insurance inspector opened the low water cutoff and told them that their policy was canceled, because clearly they never blew down this boiler. So be careful. This is near boiler piping done really, really well. And I'm going to show you a series of photographs that were posted by people that they put them on the wall at heatinghelp.com, on our bulletin board. And these jobs are just done really well. Now this piping arrangement that you see here is called a drop header. And the drop header is taking the 2 risers that go up to the header and turning them to make the header lower. And this gives you more rise out of the boiler, which is going to give you drier steam. And it also, even though it involves a few more fittings, makes it easier to make all your connections, because you got more wiggle room here to put things together, and it gives you better approach piping to the steam mains. So this continues along here. This is the part of the header, and there is the header drip and the equalizer that goes down into the Hartford Loop, which you see down here in the corner. So that's a really well done job. It's photographed before it was insulated, just to give you a sense of what's going on here. Here's another drop header. Notice that we're trying to get this pipe to go up as high as possible before it turns to go into the 2 takeoffs to the system. So we've got 2 mains, and we go off with 2 pipes off the header. One goes left, one goes right. We don't go off with one and make a turn through a bullheaded T left and right up above. And again, nothing gets connected to the system between this pipe, these 2 pipes. Here's an even nicer one. Look at this tremendous rise up here to dry out the steam, and then an oversized header to really dry out the steam, to slow the velocity, put the water back in the boiler, and the 2 takeoffs out to the system. You see the pride taken in this job. Just they paint the pipes before they insulate them. Who's going to see that except the guy that installed it? Knowing that, there's also this, and I hope you don't recognize any of your own work here as I show you these next couple of slides. But this was put in. This boiler failed because it was the sections were separated, and that was because There's no, on the header here, there's no offset. So we've got the takeoff coming out of the boiler over here. Another one going over here. There's no offset. So this pipe expanded, and this acted like a crowbar to separate the boiler sections. Notice, too, that they're doing their takeoffs to the system between the risers, such as they are, going up. So if steam's coming out of the boiler at, say, 60 miles an hour, bringing water with it, notice how the steam knows to go left as the water goes to go right, because I guess they're going to install arrows on the inside of the pipe to direct the steam this way and the water that way. I don't know how that's possible, but this guy got paid, so there. So to this guy posted this, and he's complaining about the manufacturer, Peerless, that they don't make good boilers. But look at the way he piped it. Peerless makes great boilers. But look at this. Where's the 24 inches from the top of the boiler, or even from the gauge glass? Where's my offset? You're piping in copper. All this stuff's going to come apart. How do you make water go that way if steam's going this way up into the building? So this is just nuts. But this is what people do. They don't read the instructions. Here, look here. How about this? Huh? Homemade. Look at that. Look at that. Notice how water's going to flow uphill here. I mean, this is just crazy, but this is what you see out in the field. And here, look, this is magnificent, right? Where's the header? Is that the header there? This is crazy. This is put in by a good hot water guy who never did a steam boiler in his life, but he gets to work. This one was done with no equalizer, no Hartford Loop, DWV, drainage copper, drainage fittings. And the whole thing falls apart, but the guy got paid. I mean, I once saw a steam boiler get installed with PVC plastic. Gave the woman a good price. It lasted one cycle, and then it looked like a bowl of linguine, the PVC piping. But don't, this is America. We don't have a heating policeman running around looking at this stuff. You got a plumbing inspector, electrical inspector. Nobody's looking at these steam boilers and how they get installed. You want to be good, all you got to do is follow the directions. And to show you how critical this is, I want to bring in our friends from Weill McLean, who have the good grace to bring around to the trade shows, mostly in the Northeast where there's a lot of steam, this glass pipe steam boiler. And this was done by them in Pyrex piping. They spent a lot of money on this to show you what goes on in a perfectly piped, very clean, brand new boiler. This is reality. So this is the stuff you can't see when you're not looking through glass, but this is what happens. There's your offsets, and no drop header here, but there's the steam header. This is going back into a boiler feed pump that's on their trailer. We don't have a building, so we're going to send the steam off into the parking lot. And as soon as the system starts up, notice how the water begins to come out of the boiler. And this is within a moment of the boiler starting up because of the velocity in a modern boiler. This can't be avoided. A few seconds later, the water line is up to here. A few seconds after that, it's up to there. A few seconds after that, these pipes are completely filled with water. This is normal. And it's spilling over into the header. You see the water up over here. And now we're running, and this pipe is filled with water right up to the elbows. Can you imagine if you didn't go for this 24 inches off the top of the boiler? Can you imagine if you put your header down here? You wouldn't have a steam boiler. You'd have a hot water boiler. There'd be no steam going out to the building. And it's going over here, and this is the way a normal steam boiler operates. So that's the takeoff going out into the building, or in this case, into the parking lot. You can see this tremendous amount of water being carried over and spilled back into the boiler, or into the boiler feed pump in this case. Now up here, this is what dry steam looks like. So when you're looking at a gauge glass on a boiler, it should look that dry. Dry steam is a technical term. It means that there's no more than 2% liquid water in that steam. Now, since the 80s, boiler manufacturers have not been able to produce boilers that produce that level of dry steam, which is why they encourage you or mandate you or beg you to do this near boiler piping to make sure that you're getting rid of the water before it hits the building. So that's what it should look like in the gauge glass. You shouldn't see any water spewing over the top. You shouldn't see anything floating above the water line in the gauge glass above the top. It should look dry like that, like you're looking at air. So my buddy Mike over here, he's going to do an experiment. He's going to close that valve, and he's going to build up about 5 pounds of pressure inside the boiler just to show you what happens when an automatic valve suddenly on a steam system decides to open. I'm not a big fan of motorized valves in steam heating systems. And the reason is watch what happens when he opens that valve. And this happens faster than you can snap your finger. He opens that valve and all the water in that boiler winds up in the parking lot. This goes faster than you can blink, faster than you can clap your hands. All of that water explodes out of there and it goes out into the parking lot. And the cars are getting washed and everything is... It was very dramatic. I mean, the crowds love this. And notice this fella over here coming in on his phone. He got a lesson in situational awareness when he walked right into this. So imagine this going up into a building. What the problems you'd have. You'd have uneven heating. You'd have water hammer. You'd have high fuel bills. And all because somebody didn't follow the instructions on the near boiler piping. It's so easy to be successful with this stuff. All you got to do is read the directions and do what they say. And here, they're running 2 pounds of pressure, and you can see the gauge glass is barely moving. And they cut a porthole in this, which is kind of neat because you can see what's going on inside the boiler. There's fury in there. It's like the end of the world going on in there. So just follow the instructions and you're going to be okay. And even on a small boiler, this was at another show, again, Weill McLean. This is a boiler like somebody would have in their little house. And the water's just filling right up to the top and blasting out into the parking lot. All you got to do is do what they say. And also pay attention to the water quality because water quality matters. I'm going to show you here. Here's a well-piped boiler done by a friend of mine, and it's all insulated with a nice drop header. And this Smith boiler has a skim tapping, and the skim tapping's right here on the side. It's very difficult to skim through the top of a boiler because the oil that's in the boiler when you buy it is going to cling to the metal. There's oil inside of a new steam boiler because they have to machine the boiler, and to do that, they have to pour oil all over the tools when they're drilling and tapping the connections, and they don't take that oil out of the boiler. So you got to skim it when you start it up. And there's instructions in the installation operating manual that show you how to do that. And we want to skim it from the side, and Smith's kind enough to give us this big skim tapping. And the reason why you see a T here is because my buddy who did this job knows that if he uses a T, he can fire the boiler for a day or two and then shut off the burner and just let cold water trickle in, and he could pull the plug out of that T and see where the water level is. Because without that T, you really can't tell where the water level is here, and you're liable to be skimming from where the oil ain't. So he skims into a T, and it goes into a bucket, and this takes at least a full day to do this properly. And he keeps checking the quality of the water as he's skimming it, and you could check the quality of the water by having a test pipe, and that would be say a 12-inch nipple, 2-inch diameter, and clean it up real good with soapy water so that there's no oil in that test pipe. Put a cap on the bottom of it, and when you're skimming for oil, just take a sample of it every so often and bring the water to a boil with your torch and look down the pipe and see what you got. And if it's making foamy bubbles or if it's surging like crazy, then you know there's still oil in the water. So you got to get that oil out of there. If you go on heatinghelp.com and you look in the systems help section, just search Jerry Gill. And Jerry Gill is a great contractor. I'll tell you more about him later when we talk about venting. But Jerry Gill goes into every steam boiler and he flushes it out with this special tool that he made that's just a copper pipe attached to a hose, and it's got an elbow on the end. And Jerry will go into the steam port and he will stick that copper tube back and he'll wash the boiler. And the stuff that comes out of that brand new boiler is not to be believed. It's just this black, murky water that's there from the installation of the boiler, the piping that you're doing, and also from the boiler itself, just from the manufacturing process. So watch that video and you'll be convinced that you got to clean a boiler properly before you commission it. Over here, this on the side, this is the skim tapping for this side outlet boiler here. And I like the people use our stickers over here to scare the customers. And this is the drop header that goes up over here. 2 risers going up to the header. And the pipe continues down the back. We looked at this from the other side before. And over here, they built a makeshift funnel, and they're going to clean the system on startup. And the classic cleaner in the old days was trisodium phosphate. which is a very strong soap. It won't damage anything that's in a boiler. It won't damage rubber push nipples. It's good. But in many areas where there's a concern about phosphates getting into the aquifer, it's not allowed. So instead we use a chemical soap that you could buy in any hardware store. It's called Mex. It's very inexpensive. You only need 1 pound for every 50 gallons of water that's in the boiler. So you don't need much of it. You mix it up in a bucket of hot water. And my guy here uses this funnel that he made to pour the stuff in, and he closes the valve, and then he just lets it run through the entire system, and he catches it on the return with that return line, shut-off valve, and the drain, and he gets rid of all that crap that's in the old system before it has a chance to get into the new boiler. So Mex is a good way to do it. Also, while you're at it, if you're having a problem and you're troubleshooting, check the pH on the boiler, because the pH is should be somewhere between 7 and 9. That's ideal for a steam boiler. Normal pH is 7, and that would be like milk. pH goes up on the alkaline side and down on the acid side. So if we consider something like Drano, which eats things, you know, some people think Drano is an acid, but it's not. Drano is a very, very alkaline, very, very high pH substance. And the reason why we use high alkaline with drain cleaners is because once you get over a pH of 10, it's impossible to corrode metal pipe. So that's why they say Drano is safe for pipes, because it's got a pH of about 14, but it'll eat anything that's in the pipe. So when we're making steam with water, we take feed water in off the street, and the feed water is going to contain carbonates, which is basically dead stuff, dead plant and animal life. And the carbonate just breaks down when you boil the water and forms carbon dioxide, which goes off with the steam and then mixes with the condensate on the return side and forms carbonic acid. So the tendency of a steam boiler is to move toward the corrosive side, for the pH to move this way, because carbonic acid is what you'd find in say, Coca-Cola. And that'll eat through metal. So we try to keep the pH between 7 and 9. So back in the day, the old timers used to use two things. They used vinegar and they used baking soda. And some people think that they use these two things to clean the system. Well, that's kind of crazy, because, I mean, try washing your hands with vinegar and see if they get clean, or wash your hands with baking soda. Now, these things were used to adjust the pH. So if the pH moved toward the corrosive side, which it normally would when the carbon dioxide built up from the carbon breaking down, we would try to balance it back toward neutral by using baking soda, which is a base, so it would push it this way. And if we use too much baking soda, we might get up to 10, which is okay, and that's a little high, but that's, you know, you can't get any corrosion there. But a little bit more baking soda, now we're going to get to a pH of 11, and at 11 you'll start to see this phenomenon called foaming. So there's surging, which is caused typically by oil or dirt in the water, and then there's foaming, which is caused by the pH being wrong. And foaming is water bubbles that don't break. So you got this surface of the water that forms these really tough bubbles, and it's very, very difficult to push steam through that bubble brigade that's up there on the top. If you want to see this in real life, go to any place where there's a hot tub, whether it's in a health club or in a hotel, and watch what happens when they turn on the jets on that hot tub. You're going to see this foam form all over the top, and the bubbles don't break. So you'll see kids will go in there and pick up the bubbles, and they'll put it on their heads, and they'll make little hats out of the bubbles. And I always smile at that, because what they're doing is they're sitting in water that's maintained at a pretty alkaline level. And the reason why the people maintaining the hot tub do that is because the people sitting in the hot tub often don't get out of the hot tub when they need to urinate. So they're adding acid to the water in the form of uric acid. So the baking soda or whatever it is that they use to increase the pH in the hot tub is there to counteract the pee that's in the water. So I know it's disgusting, but it's a lesson in chemistry for you. So if the pH gets too high where the boiler is foaming, they would often use a mild acid like vinegar, which pushes the pH this way and stops the foaming. So vinegar stops foaming, baking soda stops corrosion. So there you have it. That's why they use these chemicals. And if you're troubleshooting, one of the great things to use is litmus paper. You can pick this up at most drugstores. Just blow down the low water cutoff and check either with litmus paper, or you could use a pool test kit to see what you got. Pool test chemicals will also work in a boiler, pH increase, pH decrease. And it's a neat way to check that, because sometimes people add things to steam boilers that cause a problem. We're going to take a break in a minute, but I want to tell you a story before we stop about getting called to consult once many years ago on a job in a very, very fancy apartment building where they had this odor coming out of the radiators that had just started up. And the odor was unmistakably urine. And, you walk into the apartment and it just smelled like wet diapers everywhere. So I went downstairs and I met with the superintendent, who lived in the basement with his family, and I chatted with him a bit, and I said, man, it must be great working here. And he says, oh, it's okay. And I said, boy, I'll bet you get these great tips at Christmas time. People must treat you really well. And he said, yeah, you would think so. He says, but they're a bunch of cheapskates. He says, that's why they're rich. He says, the poor people will give you a tip. The rich people never give you anything. So I said, what can you do? And he says, what can you do? He says, come here, I'll show you what you could do. And this guy takes me into the boiler room, and he had this big empty can, like you'd buy at Price Club, he had an empty can, like a big Maxwell House coffee can. And all day long, he was saving his urine in the can. And before he went off at night, when they turned the heat on for the people upstairs, and it was all one-pipe steam through the whole building, he unscrewed the relief valve, and he had a funnel, and he poured the urine into the boiler, and he put the relief valve back on, and he sent it up to the people. And he said to me, that's what you can do. So I recommended that he stop doing that if he wanted to stay out of trouble. So it's a strike one for the little guy there. It was a good win for him, but it's also a cautionary tale if you're adding any kind of chemical to a steam boiler, particularly if it's one-pipe steam. Because anything you put in that boiler, I guarantee you that smell is going to come out in the apartments or in the house where those one-pipe steam radiators are. And these days, with people being so concerned about carcinogens and being concerned about health issues, if you do work on a boiler and you put chemicals in there and that chemical smell comes out upstairs, it's going to be an issue for you. The same thing goes for painting radiators. If you're going to paint a steam radiator, be sure you're using something that doesn't have any VOCs, what is it? Volatile organic compounds. The smell of the paint or whatever it is coming out in the room, because people will be very upset with you. So let's take a short break here, and then we'll get on to the next part of the seminar. I hope you're having a good time. So welcome back. Make a shift now from low pressure steam to high pressure steam. And the reason why we use high pressure steam is because you can get a lot of steam through a relatively small pipe, and it's an amazingly efficient way to move energy from one spot to another. So that's what district steam heating is all about in systems such as New York and Philadelphia and Denver, Colorado. And in other places where they use high pressure steam, they would be looking for temperature. So for instance, in your local dry cleaner, that's a high pressure boiler back there because they want to make the iron really hot. Or you may see it in a hospital where they're trying to run a sterilizer, or in a restaurant where they're trying to cook lobster, say, in a kettle. So that'll give you real hot temperatures real fast, and you get your job done. But for heating, I mean, we don't need more than 215 degrees steam at a radiator to heat people, because people are 98.6 Fahrenheit on the inside and about 85 degrees on the outside. So it doesn't take more than 215 degrees coming out of your radiator. So once the steam arrives at a radiator, we want it to be in low pressure. So if we had a system that was running off district steam, like the Empire State Building, Consolidated Edison Company might be sending that steam through the pipes at close to 200 pounds per square inch pressure. But when it gets into the building, we've got to reduce it, because we never want pressure like that to be near where there are people. So we reduce it, and there are several ways we can do that. So let's take a quick look at pressure reducing valves and some of the high points about these. First of all, this is a single pressure reducing valve, as a sketch from a manufacturer's catalog, and I want to point out a few things here. First of all, this is the sensor line that's downstream that is telling the pressure reducing valve what's going on down here. So that needs to be pitched downhill so that it doesn't fill up with water. That's important. And this is a bypass line that goes around it, and then the bypass line, we have a globe valve to create a reduction in pressure should we need to valve off this at some point to work on it and still provide steam to the building. Now, in some places, this is no longer allowed. For instance, in New York City, you're not allowed to run bypasses around PRVs. If you have to shut the steam down, you have to shut the steam down. But just a point I want to make here, that notice how it is installed above the top of the PRV and not below it. And that's, again, kind of common sense, because if this whole piping arrangement were down here underneath, it would quickly fill up with water and present a problem with water hammers. So we avoid that. 10 and 20. By this I mean that if we are upstream of the PRV with a gauge, manufacturers like to have the gauges at least 10 pipe diameters away from the PRV, and downstream at least 20 pipe diameters away from the PRV. And that's because when steam enters or leaves a pressure reducing valve, it's very turbulent, and that turbulence can affect a gauge if it was sitting right here at the point where it exits. When steam leaves a PRV, it's going a lot faster than it was going when it entered. So we want to move those gauges far enough away so that they can last and we don't shake the needles off them with this very turbulent steam. Okay, so this is a pressure troll, and the pressure troll is normally found on a boiler. That's what cuts in and cuts out at certain pressures to give us that low pressure steam. I'm showing it here and pointing to this feeler line over here because of an incident that I once came across in New York City, where they were feeding through district steam into a number of buildings that had one pipe steam radiator valves. This was a New York City housing project, and the one pipe steam, not radiator valves, but one pipe steam air vents. And the problem with the one pipe steam air vent is if you put pressure on it and continue to maintain pressure on it, the vent will work once on the very first cycle and never vent again. So that's what pressure trolls do. The main purpose of the pressure troll, by cycling up and down, is to allow the air vents to work. So just imagine, if you blew into an air vent with your mouth, that would be like steam pressure coming on. There's a float inside there, and you could blow that little float closed. And the float is not going to open again until you stop to take a breath. In cycling through the cut-in, cut-off points on a pressure troll, what that pressure troll is doing is it's allowing the system to breathe. It's allowing the air vents to work. But when we're coming off a district steam system like this, if we put a continuous, say, 5 pounds of pressure on one pipe steam air vents, they would shut and never open again. And that was the case with this one building, where they had actually cranked the pressure up to 10 psi trying to get the radiators to heat, and they kept destroying air vents, and they were replacing them, hundreds and hundreds of them, year after year after year, and it was costing a fortune. So a friend of mine who was very good at steam heat figured out a way to make the pressure reducing valve think that it was a boiler. And he did that by piping a small solenoid valve here where you see the arrow, and he wired that to a time clock, that was just pinned to open and close every 20 minutes. So 20 minutes it would send a signal to the PRV, to the solenoid valve on the PRV to say, okay, you should be closed now. And 20 minutes later, he says, now you should be open. So it effectively made the building think it was operating with a boiler that was being operated on a pressure troll. And as soon as they did that, it cured the problem of failed air vents, high fuel bills. Everything got settled, and it was terrific. So it's a good thing to keep in your bag of tricks. Now, in a building like the Empire State Building, when they're coming in at several hundred pounds of pressure, you can't just drop the pressure through one pressure reducing valve station. You have to use a series of them. And you got to go down typically in a reduction that's at least 50% across each one. So if we were coming in here at, say, 180 pounds and coming out of here at 50 pounds, and then into here at 50 pounds and coming out at 2 pounds, that would be nice. That would be a good way to go. But here's a question for you. Notice this trap that we use in here is a type of trap that is anything other than a bucket type trap. Because if we were to use a bucket type trap there, it would have to be primed with water in order to work. So you got to fill it up with water. But the challenge is when the PRV releases steam into this pipe here, it's going to be extremely hot. It's going to be superheated. So for instance, if I went in at say 125 pounds of pressure, that's 353 degrees steam. And if I came out at 50 psi, that's 298 degrees steam. So what happened to this 55 degree Fahrenheit between here and here? What happened to it? And the answer is nothing happened to it. It's there. What we have here in this pipe is superheated steam. It's steam at 50 psi that's actually 353 degrees. Now, nature won't allow that. That just defies anything that's right. So what often happens is that heat gets dissipated, the extra temperature gets dissipated, and if this is a bucket trap here that has water in it, the heat will often go into that water and cause the water to boil off, and now your trap is unprimed and it will begin to shoot steam into a return line. So not good. So this is why around PRV stations you'll usually see thermodynamic traps, which are not subject to this kind of a problem. Now, ASHRAE loves to have at least 10 pipe diameters, or whatever size pipe this is, between two pressure reducing valves. That's because, again, once the turbulence of the steam, once again, you see your gauge is far down the line from where the pressure reducing valve is, and when you come out of this, it's going to be a lot faster because the steam is at a lower pressure. So we want to make sure that we have the right size pipe, and we're always going to go into a bigger pipe there. Now, I didn't mention this earlier, but low pressure steam moves way faster than high pressure steam. It's just the nature of it. And you can see it on a chart that engineers use called a Moody's friction flow chart. And it works sort of like this. If you can imagine steam as say a line of cars going across a line. Say we had 100 cubic, or let's say 100 pounds of steam per hour to move. Now, we're talking about pounds of steam, which is a definite amount, and we're talking about an hour, which is a definite amount. So we're talking about moving a certain amount of steam through a certain amount of time. Now, the variable is the pipe size. That's going to change depending on what people decide to install. So let's get a visual example of this. Imagine 100 smart cars, and we line them up on a starting line, and we have a measured mile, and the measured mile would represent the pipe. And the 100 smart cars would represent 100 pounds per hour of steam. You with me so far? Good. Okay, so now we're going to start the smart cars, and the rule is that they're going to go bumper to bumper, and they're going to proceed along this measured mile. And since we're talking about pounds per hour or miles per hour, we want to make sure that the last bumper of the last smart car crosses the finish line at exactly the 1 hour mark. Not a minute too soon, not a minute too late. You got that? Okay. All right, so now leave the smart cars down there, and let's take all the drivers out of the smart cars, and we'll call them Mr. Pound. Mr. Pound. And we're going to walk Mr. Pound back a mile. It's okay. He could use the exercise. And we bring him back to the starting point. And we're going to put him into new vehicles now. But instead of smart cars, we're going to put Mr. Pound, all 100 of them, into 100 big yellow school buses. Now, I say that because when steam is under pressure, it's compressed, and it's really small, like a smart car. It's squeezed into a small space. Mr. Pound is squeezed into a small smart car. But when we drop the pressure, suddenly the steam expands like crazy. Just think about buying a helium balloon, and look what's inside that tank compared to how many balloons they could fill. So you drop the pressure, the steam expands tremendously, and the smart cars turn into school buses. So now you got 100 school buses, and they're lined up. So the first question is, which line of vehicles is longer? And it doesn't take long to figure that out, right? 100 school buses lined up bumper to bumper is going to be longer than 100 smart cars lined up bumper to bumper. But each one is still carrying the same pound. So what we varied here is the pressure. So now we're going to go out onto the measured mile, and the measured mile is the same mile. This is just as wide, so we're going to send these things out onto that mile. So the question then becomes, which line of vehicles had to go faster in order so that the last vehicle crossed the finish line at exactly 1 hour? Now think about it, because a line of smart cars is so long, 100 of them, but a line of school buses is way longer, right? So that means that if we're working with 1 hour as a fixed dimension in this problem, and we're working with 100 pounds, which is the 100 vehicles, regardless of their size, the line of school buses would certainly have to go way faster down that mile to cross the finish line in 1 hour as the smart cars did. So apply that to steam. When you lower the steam pressure, the steam expands dramatically because there's not as much pressure squeezing it, and it's going to need a bigger pipe because it's going to move really fast if you leave it in a small pipe. And if it moves really fast, it's going to cause velocity noise, it's going to cause erosion, corrosion, it's going to eat the pipes up. So that's why you'll always see a bigger pipe coming out of a pressure reducing valve station than the size of the pipe going into a pressure reducing valve. Got it? Good, you're brilliant. Let's move on. Down here you got a relief valve, and the relief valve is there to protect the people in the building, because if this pressure reducing valve fails, you got another one over here. Okay, but if this one fails and this one fails, suddenly you got 125 psi or more in the building with the people in their radiators. So the relief valve is there to protect people. And what we're saying here is that if the downstream pressure is going to be greater than 35 psi, let's say it's some kind of an industrial process, we would want the relief valve to pop at whatever the pressure is above 35 plus 10. So if we're having, say, 50 psi downstream, we would set the relief valve at 60 psi. If it's a heating system and we don't want more than, say, 2 pounds of pressure leaving this second PRV, that would be below 35 psi. So we would set 2 psi plus 5. So the relief valve would pop at 7 pounds of pressure. And that's, again, to protect the people. Okay, one more, the parallel reduction. And this is what you would normally see in a steam-heated building, because it doesn't get that cold every day. And on the coldest day of the year, in the middle of the winter, you need the full load of steam. But in the shoulder season, like the spring and the fall, when it's chilly in the morning and warmer in the afternoon, you need much less steam. And if you size one valve for the winter load, which is huge, and then you run that valve during the shoulder seasons, it's barely going to open. And when it barely opens, the pin is going to be riding on the seat of the valve, and that causes excessive velocity between those two seats, between the pin and the seat, and you're going to get metal erosion, and the valve will fail. So because of this, we like to split the load between two valves, and we set it up with two PRVs, and they share the load. Usually one is set at 1/3 of the total load, the other at 2/3 of the total load. And then we have it set so that the larger pressure reducing valve is 3 psi lower than the smaller one. So it's handling the load as well as it can until it can't anymore, and then its downstream pressure begins to fall off. The big PRV senses that, and it jumps in to help its little brother, and they then share the load for the winter. And when the spring comes around, they go back to doing what they did. So that's a typical way that it's done in a steam-heated building. Now, steam-to-water heat exchangers. Now, many buildings, particularly modern buildings, work with both steam and hot water. For instance, in cities like New York, you'll see very tall buildings where they'll use either Con Ed district steam, or they'll have steam boilers that send steam up to tremendous heights. And about every 10 floors or so in the building, there'll be a completely independent hot water heating system. And that could be operating radiators, it could be operating fan coils, or it depends on the system. Take, for instance, the new One World Trade Center. That takes steam off of Con Ed because of its height, and every 10 floors or so, there's a completely independent steam-to-water heat exchanger that feeds into radiators that are on those buildings. Reason being, if you take a building that is that high and try to run it on hot water, the static weight of the hot water over that tremendous vertical distance is going to be so enormous that you'd have to have really specialized equipment in the basement to take the pressure of the weight of the water. It's like going deep sea diving. So steam, which has literally no weight when it's moving through pipes, goes up, and it carries a tremendous amount of BTUs needed to go into the heat exchanger to transfer the heat from the steam to the water to heat the building. It's a classic way of doing it. It's been around for a long, long time. So some tips about this. Here we've got the steam line coming in. It's going into a steam regulator, which has some kind of a temperature device, and this could be self-contained, it could be electric, it could be electronic, it doesn't really matter. Over here we've got the water side, and let's say we're heating radiators with this. So this is the return coming back from radiators, and it goes into a copper coil that's inside this cast iron shell or steel shell, and it comes around and it supplies out to the radiators. And this is the shell, the tubes are inside, and we're going to send steam around the outside of the tube. The steam's going to give up its latent heat energy to the flowing water. The condensate forms, and it goes through a steam trap. This is a service valve, and it goes into a condensate pump that just fills up with condensate and dumps through a check valve, through another service valve, back to somewhere, back to a boiler feed pump, or maybe even into a boiler. This is vented to the atmosphere. So the steam is pushing the air ahead of itself. The air comes through the trap, through the receiver, and out the vent. Now, what's absolutely critical here is this vacuum breaker, which is in the side of the shell. Now, I say it's critical because when the regulator shuts, the steam beyond the regulator is going to condense and shrink 1,700 times in volume. So you're going to get a vacuum forming inside this. It's kind of like holding a straw in a glass of water and putting your finger over the top of the straw and lifting it out of the glass. The water stays in the straw, right? Why? Water stays in the straw because it's a battle between the static weight of the water, gravity, inside the straw against the atmospheric pressure that's against the bottom of the straw holding it up. So we need to get atmospheric pressure into the top of the straw by lifting your finger to make the water fall. That's what the vacuum breaker does. As soon as vacuum begins to form in there, the vacuum breaker opens to allow air into the shell, and then the weight of the water in this pipe pushes the steam condensate through the trap and into the condensate pump. Now this is why you'll often see these shell and tube heat exchangers mounted up high on a rack and the trap way down low. Because when the regulator closes, all we have to push the condensate through that trap is the static weight of the water. Remember, we have no more steam pressure at that point. There's just atmospheric pressure inside the shell allowed in by the vacuum breaker. So we want to get this trap as low as we possibly can below it. If the trap is too close to the outlet, for instance, last year I looked at a problem that somebody had shown me where a coil kept freezing, and they had cold outside air moving across this coil, and they had installed the trap right at the bottom of the coil. So when the control valve on the coil shut, the water, the condensate, just stayed inside the coil, and the cold air kept moving across it, and it kept freezing the coil until finally somebody realized that that trap was way too close vertically to the bottom of that coil. They lowered it and it solved the problem. So this is when we've got a vacuum breaker and a steam exchanger, and everything is pretty simple here. Let's make it a little bit more complicated, because what's going to happen if we don't get the water out of that shell, it's going to get hit with water hammer, because the water will lay inside the shell, and the next time the steam enters, it's going to take that water and bounce it off the back of that shell. It's going to turn around, it's going to hit the tube bundle and put holes like that in your tube bundle. And that happens all the time. And that'll happen on the very first cycle. It's not like something down the road. This will happen the very first time you start it up in a steam-to-water heat exchanger. So the vacuum breaker is absolutely necessary in these applications. Let's make this a little bit more interesting. Here we're heating domestic hot water in this big tank, and we're going to have what's called a bayonet heater sticking inside of the tank. And we're reversing it here because now the water is inside the tank and the steam is inside the coil. So the bayonet heater is just this big trombone-like device that goes in there, and it steams inside of it, and it turns around. The condensate comes back by gravity, and it's flowing down through a trap. And in this case, we've got a check valve. And over here on the steam supply line, we have another trap and another check valve because we decided to give this one an overhead return, just to make it more interesting. So the steam's coming down, because steam doesn't know up from down, it just knows out. It's looking for an air vent. And we're going to send the steam through a regulator, which is sensing the temperature of the water in the tank. And the condensate's going to come out. And as long as that regulator is set properly and it's high enough in pressure, we can lift the condensate through the check valve and up. You need 1 pound of pressure to lift water about 2 feet. So if this were a 10-foot lift into the overhead return, we'd need at least 5 pounds of pressure to get that job done. But what happens when the regulator closes? Suddenly we don't have any pressure here because the steam is off. So the check valve is closed, and the weight of the water in this pipe is keeping the check valve closed. The weight in the water in this pipe is also keeping this check valve closed from the trap that's draining the steam that forms on startup in the steam main. So now the steam condensate is going to flow back into that trombone-like bayonet heater, and the next time this regulator opens, you're going to get water hammer inside that, and it's going to cause that same problem we looked at earlier. It's going to bust the tube. So to keep that from happening, the classic way is to use what's called a spill trap. And that's just a standard 3/4 inch floating thermostatic trap that's mounted about 4 inches higher than your operating trap, and this spills to a drain. So normally this is closed. When the regulator is operating, the steam goes right by it because the trap is closed, and you get your lifting of the condensate, and life is good. But when the condensate starts to back up after the regulator shuts, it's just going to open that trap and spill out. And on every cycle, you lose a little bit of water, but it's better to lose a little bit of water than it is to lose a tube bundle on every cycle. So that's an old-time trick, and it works like a charm. All right, so now we're covered with that. We're done with that. Let's look at all different types of system piping that you would find on steam heating systems. And we'll start out with the most basic one. and that's called a one-pipe parallel flow with a wet return. Now, by wet return, I want you to notice this dotted line here, because that's the center of the gauge glass, and everything below that dotted line is underwater. It's always underwater. So we call it a wet return. There's the Hartford Loop, and this is one-pipe steam. You can see the vents on the radiators, graphically anyway, and a main vent near the end of the main. Now, the pitch has to be 1 inch and 20 feet in the direction of flow, which isn't much, but when we have parallel flow, meaning the steam and the condensate are both going the same way, the pipe has to be at least 1 inch and 20 feet. What I want you to watch out for is the loss of that pipe, and that often happens over time, when hangars settle, or if they've had asbestos removed and the abatement people came in and removed the hangars and didn't properly support the pipe again, or if people hung things on pipe. I often see people do this, and even at homes. I remember looking once at a guy's house where he bought a heavy bag, like a boxing bag, because he wanted to get in shape, and he hung the heavy bag, which was filled with a lot of sand, on a steam pipe, and it caused the pipe to sag. And he's down there banging away on the heavy bag, and the pipes are loaded with asbestos too, so he's getting healthy. Every time he hits the bag, he's sucking a lungful of asbestos. Nice. But it caused the pipe to sag, and his complaint was he suddenly had this wicked water hammer that he never had before. And I asked him when it happens, and he says whenever the system first starts up. Well, if you can imagine, you hang a heavy bag like right here, and it's hanging down. It's got a couple hundred pounds of cement, or not cement. That would be bad for your fist. Sand inside of it, and the pipe takes this sag. So on startup, the water is stuck in the sag because it can't drain. Because water won't drain downhill if there's no downhill. So the next time the system starts up, you get water hammer on startup. So that's why I'll always ask when it comes to water hammer, when do you hear it? And if you're hearing it on startup, the first thing I look for is the pitch of the pipes. Did we lose it? Whether or not they took off insulation and didn't replace it, because every steam pipe ever made is supposed to be insulated. And if you remove the insulation, you're going to get a lot of startup condensate when those pipes are going from ambient temperature to 215 degrees. And often that excessive amount of condensate in the pipe that was not designed to handle it, because the pipe is supposed to be insulated, will create water hammer. Too much water, too much steam in a pipe, you're going to get banging. So I'll always ask, when they tell me to have hammering, not just what does it sound like, but where is it, when does it happen, and where is it coming from? Whereas another thing, because if the system is running for a while and then you start to get hammering, and it's happening down here at the end of the main, look at this thing called the A dimension, which I'll explain in more fully in a second. But the A dimension is the distance between the bottom of the lowest horizontal steam carrying pipe and the boiler water line. And that is designed to put the water back in the boiler. Depending on the weight of the water in this pipe, combining with whatever steam pressure is in this line, to put the water back in the boiler. That's why we call it gravity return. If the pipe gets clogged here, the wet return, and it will, because this is an open to the atmosphere system, so at some point this is going to fill up with mud. When it fills up with mud, the water is not going to be able to shove its way through that mud, so the returning condensate will just creep up here and peek its little face over the end of this line, and when Mr. Condensate meets Mr. Steam coming down at that line, Mr. Steam wins. And you start to get this banging, smashing water hammer, and it's always going to happen near the middle of the cycle. So that's how you know what's causing it. That's when you begin to suspect that these pipes are suffering from the steam version of arteriosclerosis. So about that A dimension, as I said, it's got to be 28 inches from the boiler water line to the bottom of the lowest steam carrying pipe, wherever that is in the building. And here's why. When we're operating, let's say that there's 2 pounds of steam pressure inside the boiler. Now, when the steam leaves the boiler, it loses energy due to friction and by condensing. So by the time we get out to the end of the main, we're not going to have 2 pounds of steam pressure left. That's impossible. This is not like you're dealing with compressed air. This is steam. It's going to change state. So by the time it gets out to the end, even in a big building, we may have 1.5 pounds of steam pressure. Now here's the problem. Think of this as a scale. You got 2 pounds of pressure on this side of the scale and only 1.5 pounds of pressure on this side of the scale. So the tendency is for the water to push out of the boiler and go up this line. So let's accommodate it. This is where the A dimension comes in. We're going to give it a vertical distance that's equal to 28 inches. Now a column of water 28 inches high happens to exert 1 pound of pressure at its base. So if I've got 1 pound of static water weight and 1.5 pounds of leftover steam pressure, that gives me 2.5 pounds on the return. There's only 2 pounds of pressure in the boiler, and that's how the water is going to flow by gravity from the high pressure into the low pressure, relatively speaking, of the boiler, and that's how we get the rabbit out of the hat. So that's what the A dimension is about. You need to measure this. If you're moving a boiler and you see that the boiler's in a pit, that's probably why the boiler's in a pit, so they can get it low enough to provide the A dimension. If you decide to put the boiler out of the pit, you might have water hammer after you're done working, like they never had before, like you won't believe. Now, since return lines do clog up because systems do corrode, many of the old-timers use parallel flow with a dry return, meaning that instead of dropping directly into the wet return and coming back this great distance underwater, we're going to come back above the water line and pitch 1 inch and 20 feet both ways. But notice now how your A dimension is no longer out here at the end of the main. It's now shifted over here back in the boiler room. And once again, this may be the reason why the boiler is down in the pit. So when you're changing a boiler, you have to wander out in the building and find that lowest horizontal steam carrying pipe and measure from there down to where your new water line is going to be. And here too, you see this loop where we drop down to go into the Hartford Loop? The reason why we drop down like that and form a P-trap is if we just came directly back into here, the steam in this line, as the boiler steamed down, could have access to the return, meaning the condensate coming back, and that would give you water hammer here during near the end of the cycle. So we always drop down to the bottom and come up into the Hartford Loop. And please provide some valves here, because I guarantee you that all the schmutz in the world is going to wind up in that U-tube right there. And when that happens, you're going to get water hammer here. So much of this is common sense. It's just think like steam, think like water. What would you do? That's what I'd do. One pipe counterflow is a very unusual system that's found in buildings, smaller buildings. This line that runs out that carries the steam and the condensate in the same direction is usually never more than 100 feet long. So we're feeding one pipe steam radiators, and the pitch now has to be double. With the other systems, we needed 1 inch and 20 feet. Here we need a minimum of 1 inch every 10 feet. And the pipe has to be bigger in size too. So if you're not sure what size pipes you need, get a copy of my book, The Lost Art of Steam Heating, or get a copy of my book, The Golden Rules of Hydronic Heating, because in that book I show every pipe size in every steam system and the maximum load that could be on that. So if you're having a problem with water hammer on a job like this that's one pipe counterflow, you would go out and you'd measure the radiators for their total EDR load, and then you would look at the size of the pipe to see whether the size of that pipe in this system could handle that radiation load, because it might be that somebody added radiators to the line over the years, and that's why it's having a problem. That's why you can't get heat, or that's why there's water hammer. And here again, notice how the A dimension is back here in the boiler room. So feeding steam, doing the near boiler piping for what the boiler needs according to the manufacturer's specification. We're feeding into the top of this main and dragging the condensate down the bottom of the main, so counterflow. The Mills system, Mr. John Mills, that genius who worked for the H.B. Smith Company. This is what he did with this job where you got one pipe steam in a big tall building. Say it's a 10-story building. You come out of here with what might be a 12-inch screwed pipe. You go all the way up to the top. You put a big air vent up there because you want to vent all the air out of that big 12-inch pipe. Imagine a 10-story building with a 12-inch pipe inside of it. That's a lot of air. So vent the air very quickly out of there. The steam's going to get up here real fast. Vent the air out of here at the end of the main that goes around the perimeter of the upstairs, and you're going to get rid of the air out of that, and then you down feed, because steam doesn't know up from down. It's just looking for an air vent, and it finds them on the radiators, and it finds the air vents at the base of the risers. So the steam's going to go chasing toward the air vents. Your A dimension is now the distance between the boiler water line and the bottom of your lowest main vent. So the Mills system, it was a beautiful way of heating tall buildings with one pipe steam by getting everything up to the top and then down feeding to the radiators. Steam does not know up from down, it just knows out. It's looking for high pressure going to low pressure. Now in some of the bigger buildings, they wanted to use two-pipe steam. I gave you some examples earlier about the advantages of a two-pipe radiator. It just feels better. Plus you're able now to throttle the inlet valves, so if you want the radiator to heat partway, you can shut down a little bit of the steam. If you want it all the way, you open the valve. One pipe steam was open or closed on the valve. You can't control that, but here you can. So in many buildings, they gave us this option, and they would now have thermostatic traps on the radiators, like that one I showed you in the New York Public Library that had the pneumatic system in it. And at the end of the main, we have float and thermostatic traps, which will stop the steam from moving through the end of the main into the dry return, because if it wasn't there, steam would go down the end of the main, and right into the dry return, meaning the condensate coming out. You destroy the trap, and you'd have water hammer. So F&T traps stop the steam here. Thermostatic traps stop the steam there. We have a main vent at the end of the main. Steam pushes the air through the traps. Before it can trap steam, it must vent air. It vents air into the return line and out of the main vent. Now over here, I'm showing you, instead of an A dimension, what I call a B dimension, which is the distance between the end of this main and the boiler water line. Since there's no steam pressure in this return line, because of the F&T trap, the only thing I have going for me to get back in the boiler is the weight of the water. And if there's 2 pounds of pressure in the boiler, I have to have at least 30 inches of static weight here per pound. So a little bit more than 28 inches. So I would have to have, say, 60 inches of height here of water to build up in order to push through a boiler that's operating at say, 2 psi. If I didn't have that, the water is going to back up into the main. That's 5 feet, right? The water is going to back up into this return main and close the air vent. It won't hammer because there's no steam in this line. But if somebody came along, the superintendent, and cranked the pressure troll up, the water is going to back up here and flood the air vent. So now the whole building goes cold. So when I was younger and I was doing a lot of consulting, I would go out and I had this special screwdriver. I was one of the few people in New York who had this. It was a counterclockwise screwdriver. I was able to go up to a pressure troll and turn it counterclockwise to lower the pressure. Most everybody had clockwise screwdrivers. All they knew to do was to raise the pressure. And in raising the pressure, they flooded the main vents. So I would go in, I'm this consultant, right? They're paying me a lot of money. I'd go in, I'd see the traps on the radiators, I'd see the traps at the end of the main. I would see no condensate or boiler feed pump. I would recognize it as a 2-pipe gravity return system, and I would take my counterclockwise screwdriver and screw the pressure troll down. That would cause the water to recede. The water would go back in the boiler because the pressure is now low. The main vent would stop being flooded, and the whole building would heat. And they would say, all you did was screw the pressure troll, and suddenly everything's working. I said, that's right. They said, well, why should we have to pay you for that? I said, because I knew that it needed to be screwed down. That's why you have to pay me for that. And your guy didn't know. So keep that in mind, right? Now here's a 1-pipe pumped return system. Let's say we don't have that static weight. We don't have enough weight, 30 inches per pound. So it's a 1-pipe system, and we've got a condensate, a floating thermostatic trap at the end of the main here, and another one over here. And here we got a condensate pump. So condensate pump is kind of a rude machine in that it doesn't care whether the boiler needs water or not. It has a float inside of itself, and the float is connected to this pump, and there's a vent on it. So this is just this big receiver, and there's a float inside. The float goes up, it turns on the pump. There's a check valve here. It pumps the water through the check valve. We don't need a Hartford loop here because there's a condensate pump. When you got condensate pumps, you don't need Hartford loops. We do need the equalizer because that's picking up the carryover water that you showed in that glass pipe boiler, or you saw in that glass pipe boiler before. So we're going to pump into the bottom of this, and that's fine if the boiler can accept that water as it comes back, because this condensate pump is not asking this boiler whether it needs it or not. But the challenge comes about when you put in a modern boiler, which is much smaller than the boiler you're replacing. So it's smaller and it has a lot less water in it. And the question then becomes, will the condensate pump, acting as it does, by not asking the boiler whether it needs it, will that be able to flood that new boiler? And if you suspect that it might, what I suggest you do is don't use a condensate pump here, but switch over at that point to a boiler feed pump. Now, a boiler feed pump has a larger receiver, as you see here, and it also has a pump controller, as you see here. So now what's controlling this pump over here is the pump controller, which senses the boiler water level, not the water level inside the boiler feed pump. So it's got an oversized receiver that can collect and store any water until the next cycle when it's needed. And the only way water can come into this boiler is if the boiler actually calls for it through its pump controller. So this is a good way to prevent that flooding problem, or solving the flooding problem if you have it. Replace the condensate pump with a boiler feed pump. A 2-pipe vacuum system now. Let me just back up a minute and explain something about vacuum system, because earlier I told you about Andrew Pohl and that system that he invented that was at the Dakota apartment house and the old post office in New York, which is now Donald Trump's big hotel. But the naturally induced vacuum system would happen with ejectors, where they would where they would suck the air out of the system. That was the pole system. And as time went by, they invented these types of air vents that would go on radiators. And the air vent would have a little check valve in its outlet. And the main vents that went at the ends of the mains or near the ends of the mains had little check valves at the outlet. So the steam would come on, and it's a coal-fired system, and it would slowly nudge the air out of the system, and it would push out through these check valves on the air vents, and then when the steam condensed, the check valves would seat and not allow the air back in. So the entire system would go into a vacuum because the air couldn't get back in. Now, in the days of firing coal, that was very desirable because the coal fire was not steady. You know, it burned down during the day as the coal went down. So imagine back, you know, before we had gas barbecues and you were doing everything with charcoal briquettes. You make a fire, you cook your burgers and your hot dogs, and comes a point, you know, somebody shows up late for the party and you're out there trying to make one more hot dog, and you're standing there waving a newspaper trying to get those last coals hot to give you enough heat. Well, that was the challenge they faced in the coal-fired days, because as the fire burned down, there was less and less energy going into the water to make steam. But if they could use these naturally induced vacuum systems that would send the air through the check valves and not allow back into the air vents because of the check valve seating, they would be able to boil water at temperatures that got lower and lower as the vacuum formed. So later in the day, you might have steam leaving that boiler at temperatures like 150, 160 degrees going up to the radiators because the system would be in a tight vacuum. That got abandoned when we moved from coal to oil and gas, because now that you've got an automatic burner, when the thermostat shuts off the burner, the vacuum forms very, very quickly. And it often forms on the first cycle before most of the air is out of the system. Remember, steam and air are different densities and they will not mix. So if you didn't vent all the air out, in the presence of the vacuum, the air will just expand into the vacuum and actually block the steam from moving. So they got rid of these vents as time went by, and now we have very, very few of these naturally induced vacuum systems still out in the field. The big buildings used vacuum pumps, and this was a great advantage because you take a building again like the Empire State Building, which is running off Con Edison district steam, operating at 2 pounds of pressure, and it's got a vacuum system in there, which means that we have a pump here that inside of itself as an ejector, like we used in the old days with the steam engines, and it will shoot condensate through the ejector and form a vacuum. And the vacuum is formed by sucking the air out of the return lines, through the traps, out of the steam mains, through the radiators, all the way back to the boilers. So this guy is going to suck the air right back to the surface of the water in the boiler. The burner comes on, the system begins to go into vacuum, and suddenly the steam begins to chase this vacuum that's forming. And because we've got this greater differential going from a very low pressure, relatively speaking, say 2 psi, into what might be a negative 3 or 4 psi on the vacuum side, there's your greater pressure differential from one side to the other, so the steam goes faster. High pressure goes to low pressure. So the steam begins to move more quickly throughout the building. So it was a great way in a really big building to get the steam out to the extremities and to get the radiators hot. And also because they were working with the steam pressure to vacuum differential, they also got to downsize every pipe, valve, and fitting on the job. So, for instance, if you needed a 3-inch pipe, well, you get away with a 2.5-inch pipe. Everything went down by at least a half a size, which means that once this thing is a vacuum system, it's always a vacuum system. You can't run it effectively as a pressure system, just trying to push the steam out rather than pulling the air back. Well, you can, but at great expense and with tremendous amount of problems. So, this is the challenge we run into. Steam traps don't last a long time. I mean, manufacturers took, maybe 10 years, maybe 5 years, depending on how the building is being used. But when a steam trap on a radiator dies, it just begins to pass steam into the return line. So now you got steam here. If the floating thermostatic trap fails, you got steam here. The steam is heating the condensate, making it super hot. And this vacuum pump is making a vacuum. So in the presence of the vacuum, if the water is too hot coming to it, the pump's going to come on and it's going to cavitate. It's going to flash water into steam inside of its impeller, and it's going to fail. So we got to figure out a way around that. And the way around that is to maintain the traps. Make sure your traps are working. But the problem in reality is that the big buildings, they don't know if they have a good maintenance program or if it's a cooperative apartment building. Some people have heat, some people don't have heat, some people are complaining, other people are not. So they don't do anything. They wait. They wait another year. And in that time, you begin to get to a point where the vacuum pump has just failed. And now somebody will go downstairs, and on the vacuum pump, there's a switch that says pump only. Now it turns this vacuum pump into a condensate pump, but it's not making vacuum anymore. So everything in the building is screwed now. I mean, there's no distribution, there's high fuel bills, there's water hammer, there's complaining people, and they'll bring in another contractor. And the other contractor will come in and he'll do something like this. He'll go out and he'll buy a trap, a really, really big trap. It's called a master trap. Anybody that does this is a world-class knucklehead, because what's going to happen now is the vacuum pump is going to pull a vacuum between here and the trap. That's it. And you get this beautiful vacuum here. Now over here, you have now double trapped your return lines. So some of these traps are working, some aren't. When you double trap a return line, nothing moves through it. So the water lays back up here in the system, and it's hammering like crazy. And when it finally does work its way back, if it works its way back, if enough traps fail, this guy then opens up and vomits this super hot water into the vacuum pump and blows it up again. There's so much for Mr. Master Trap and the knucklehead who put it in. So this is never accepted. Don't get sucked into that. This that you see here is a check valve that's just facing this way on a pipe that goes down and fills up with water. Now it's that way because on a system in the springtime or in the fall, when again you got chilly morning and the steam comes on cold pipes, it's possible that just the steam condensing in the pipes on the supply side could induce a deep enough naturally induced vacuum that would be deeper than what the vacuum pump is making on the return side. So in other words, you could have a deeper vacuum on the supply than you have on the return. And when the traps then open, nothing's going to move. The water will just lay in here. In fact, everything will start going backwards. So this guy, this vacuum breaker, this check valve that's under a water seal, prevents that from happening. Because if a vacuum over here begins to form, this breaks it. So this is the vent line that's going over here, and it connects to the steam header. The two-pipe air vent system that I mentioned earlier, this is what we had at many of the buildings. The Dakota apartment building had this. It was converted to this one. They went away from the pole system. And this is where you'll see one size larger. So it's a supply pipe to a radiator. And this is the return line. In this case, everything's going into wet return. So two-pipe air vent system. Air vents on every radiator. So it's kind of like one pipe steam pitched in the direction of flow toward what are essentially drain lines that go back into the return. So in this case, you'll know it because the supply side is always going to be one size larger than the return side. Here you see it in real life. This is the supply over here. Look at the size of the pipe. One size smaller over here. And the air vent is always on the return side. So it's a one-pipe steam system with a drain. They were used in government buildings and schools and in places that had big radiators, and we didn't want counterflow in the supply main. So two-pipe air vent system. It's the one time when you will see, and they belong, air vents on a two-pipe radiator. Other than that, if there's a steam trap on the radiator, it should never have an air vent on it. This is a two-pipe air vent system in a Manhattan office building. Now, this one was fun because this is the supply line. It's a vertical riser that goes up through the 12 or 13 stories on this building. This is the return line. Notice how this feeds the radiator. Now, they decided to use these thermostatic radiator valves, which was a big mistake. This is feeding the radiator. It goes over to the other side of the radiator and in. This is the return from the radiator. This is going into the main. Now, there is steam in this line, and there is steam in this line. This is normal for a two-pipe air vent system. It's kind of like a ladder where the steam is moving across the rungs. There's nothing to stop it. The rungs are the radiators. So the steam is on the left side of the riser, the radiator, and on the right side. So the steam favors the supply pipes because they're bigger on startup. Once the system is running, there is steam pressure in both of those lines, and it's feeding toward the radiator, and the radiator works because it has an air vent on it. See the air vent right there? That's why the radiator works. Now, they put a thermostatic radiator valve on here to prevent the radiator from overheating. It sensed the room temperature, and it closed. It did its job. So this steam line was closed. But there's steam in this pipe, and there's an air vent on the radiator. So, the radiator just shrugged its shoulders. The steam went into the return, heated the radiator, pushed the air out of the air vent. So the radiator continued to heat. So I got involved in this, and I said to the people, you got to get rid of these. You can't use this type of a thermostatic radiator valve on a two-pipe air vent system. You have to use the type that goes between the air vent and the radiator, as I showed you earlier. And they said to me, well, who's supposed to pay for that? I said, I don't know. That's not engineering. That's sociology. That's something you're going to have to work out between whoever you hired to do it. But this was definitely a mistake. So, again, know what it is that you're looking at before you get involved in it. If you see pipes like this and you don't know what you're looking at, take pictures of it. Go to heatinghelp.com, post the pictures on the wall, and somebody will tell you what it is that you're looking at within minutes. Why should you muddle around in the dark making mistakes when answers are as close as your computer? Believe me, I learned this the hard way. So here's a boiler that's mounted up on a very high platform. The first time I saw this was in an apartment building on Long Island, and I went there with a contractor who was changing the boiler, and he brings me down the basement, and we're looking at this big cast iron boiler that's sitting up on what appeared to be an altar, and it must have been 5 feet in the air, and the boiler's way up there. And the building's at the top of a hill. And the guy says to me, "What? I don't know why they put it up here. Whether they're afraid of floods or something. I mean, it's never going to, if it floods up here, that we're going to need Noah." So we had a laugh. And he says, "Can I put the boiler on the floor?" And I said, "Sure, I don't see why not." Because, I wasn't thinking. I was young and dumb. So he puts the boiler on the floor. What I didn't know was this guy who put this boiler in was brilliant, because he was creating what's called a false water line. Now he's going to create a false water line when we move it, but right now look at the water line of the boiler. It's sitting up on this pedestal about 5 feet up, and this is a one-pipe steam system. This is an apartment building. This is the lobby. There are doors in the lobby that go into offices and whatnot. And every time we get to an office, the pipe dips into the concrete floor and comes up on the other side. So as we go through, we're going under these doors and back. Now, by mounting the boiler up so that its water line was about a foot higher than the lobby floor, he put all of those pipes permanently underwater. So the steam line was here. This is the A dimension, and everything here is a wet return. Got it? Okay, now, my guy says, let's put the boiler on the floor. So he says, okay, put the boiler on the floor. Look where the water line is now. Now it's down here. We just took what was once a wet return and turned it into a steam line with all these pockets that go into the doorways. Well, the first time they run it, the pockets were full of water, and the steam came bellowing through here and took that water and just hammered it, and the hammering was so loud that you could actually hear it outside the building. I've never heard anything like this. And the guy called me up and he says, "What do I do?" So at this point, I do some research, which I should have done in the beginning, and I learned about this phenomenon that the old-timers use called a false water line. And a false water line is a trick that we're going to use to make the building think that the boiler is where it used to be. So we do it by taking this pipe here and getting rid of it. We're going to get rid of that pipe, and we're going to create a dam by making this pipe go up and down into the Hartford Loop, and then we're going to take some steam and put it into this side, because we've got a U-tube here. You see it? U-tube, this is filled with water all the way across, because now the water line is up here, not there anymore. So this is a U-tube. So there's steam pressure on this side pushing down, and I want some steam pressure on this side, so that the steam pressure over here doesn't blow this water seal. Because without steam pressure over here, it's like a seesaw where you take off one of the kids. This guy's going to go up. So this solves the problem. And that's what we did. It was either that or put the new boiler back up on the 5-foot altar. We didn't want to do that. Now here's an example of this. I want you to follow this old wet return. This was coming in. Now the old boiler water line used to be up high like this. The new boiler water line is down here. So if you follow this arrow across here, you can see how high that is on the gauge glass. So without the false water line, this definitely would have been a steam line. It would have hammered like crazy. So to avoid that, we just bend it up like this. We create a dam. So now the system thinks the water line of the boiler is over here. We spill over here. It sounds really pretty too. It bobbles over the top. It sounds like new age music. And we threw a little air vent in here just to get the air out in the initial startup. That goes down into the Hartford Loop. And here's the steam line to equalize the pressure from the end of the steam main, pushing down on the other side. And it worked like a charm. So when you see stuff like this on jobs, just know what it is that you're looking at. So here's a return line coming back, and all of a sudden the pipe just deeks up like this and comes down like that. And you look at that at first, you say, what, are these people crazy? No, they're not crazy. They're building a false water line. There's an air vent right there. So the building thinks that that's it, and all those pipes that are in the lobby level of the apartment building that go under doorways, they're all permanently put underwater by building this false water line. Now, I mentioned earlier that all steam pipes need to be insulated, and it's a good idea to also insulate the returns as well, because there is in science something called Henry's Law, named for William Henry. If you ever take my hot water class, I'll tell you a lot about him, because he's got a lot to do with air separators and compression tanks. But William Henry was the guy that told us that gases dissolve in liquid in proportion to pressure and temperature. And on the return side of a system, when the condensate is allowed to cool too much, it begins to absorb that carbon dioxide that's in the system as a natural product of boiling water. When you boil water, you get carbon dioxide. And the carbon dioxide mixes with the condensate to form carbonic acid, which eats return lines and causes them to leak. But if you can maintain the temperature, to keep the water temperature hotter in the return lines by insulating them, you'll have less corrosion. So it does pay to insulate return lines, even though there's no steam in there. On the supply side, on the steam supply, it really pays to insulate, because if you don't, you turn your steam mains into radiators, and now suddenly you need a bigger boiler than you used to have. So this is asbestos. It's very dangerous. We've got to get rid of it. We don't do it ourselves. We bring in people that know what they're doing. Years ago, we didn't know what this was. We didn't know it. Well, we knew what it was, but we thought it was nice. And we used to throw that at each other when we were in boiler rooms. We made snowballs and just have lots of fun with it. So we got to replace that with fiberglass. And the fiberglass is safe and looks like that. So this will give us a better way to keep the steam on its way to the radiators, rather than condense in the piping that's in the crawl space, in the garage, and inside the walls. We want the steam to be in the radiators. Now this chart here shows us the bare heat loss from horizontal bare steel pipe. So this is what happens if you remove asbestos and don't replace it with fiberglass. Let's say we've got a 2.5-inch steam main. That's this here. Now this chart is just showing us that the steam would be at about 215 degrees. So we read up to this line, and we see that the BTU loss per foot is about 260 BTUs per linear foot when you remove the asbestos and don't replace it with something suitable. Now a square foot of EDR is only 240, so your pipes become better than radiators as soon as you remove that. And your boiler is now heating crawl spaces and garages where there's no people, and inside walls where there's no people. It's crazy. So it pays to insulate pipes. Now this shows you how much. There's a lot of numbers here. I'll just look quickly. It's number, blah, blah, blah. We go through some math here. We figure out the difference, and it's 49 BTUs. If we have just 1 inch of fiberglass on that pipe, it drops from 49 BTUs. Without it, it's 260 BTUs. So it's more than 5 times the amount of heat loss when we remove the asbestos and don't replace it with something as simple as 1 inch. The more insulation you use, if you use 2 inch, it gets better. But the more you insulate, the better everything is. The quieter it is, the faster it is. It's just good for steam system. Now, I love talking about this part because it's probably the most important stuff in all of steam heating. It's venting. Because steam and air are gases that have different densities. Where there is air, steam will not go. So we got to be able to vent the system every time it starts up. So let's talk about the air vents. This is a very common air vent. It's made by Hoffman Specialty. It's called a number 40, and I show it to you because there's so many of them out there. Now it's got this little piece that sticks inside the radiator that is appropriately called a tongue. And the tongue is there to let the condensate that gets stuck in the radiator vent, the drain out. It just dribbles along the bottom of the tongue back into the radiator. This is a float that has a flexible bottom, and the float is partly filled with a mixture of alcohol and water, and it's sealed. And when steam hits this, it causes the stuff on the inside to boil. And when that boils, it expands and it pushes the bottom part out, so the bottom pops out and it drives the pin up into the seat. At this point, the vent is closed. And this is kind of like hanging in space because it's sitting up there. And even when it cools off, it's still hanging in space because the steam pressure is pushing against the bottom of it, keeping it closed. So what we want to happen is the float to fall so that we can have venting again. And that's where this thing called drop-away pressure comes in. Vent valve manufacturers in their literature, they call it either operating pressure or drop-away pressure. And it's the pressure through which the system must cycle down at the end of every cycle. And that's where the pressure troll comes in. So drop-away pressure works like this. Let's say you're starting up and you got steam pressure. So you get to 2 psi or 5 psi, whatever you're running. And you're pushing with relatively low pressure against a big wide bottom. and that is shutting the vent. Now, that's being opposed by atmospheric pressure that's trying to fit in through this little hole. So it's kind of like what makes a car lift in a garage work, right? You got a big surface, big piston, small piston. This is trying to push down. This is pushing up. So when you got steam pressure on here, if it's on there all the time, this is going to keep the vent closed. Stays closed all the time. That was the challenge that we had with that New York City housing project that was taking Con Edison steam, which came in at a constant pressure and never dropped. The constant pressure just held the vents closed. And before the air is out, the radiator is full of air. Steam's trying to get in. The radiator won't get hot because the air can't get out. So we want to lower the pressure so that the weight of this float can overcome the closing force and venting can continue beyond the first cycle. So that's called drop away pressure. We got to get below that point. Now, back in the day, companies like Hoffman Specialty made vents like this. Now, this was a main vent. Look at the size of this thing. It's 10 3/4 inches high with a 3/4 inch tapping. This is an air vent. This thing is like a car muffler. And you just imagine the massive amount of air that this thing could vent. And this was developed during the time when we began to move away from coal and toward the automatic fuels of oil first and then natural gas afterwards. Because those automatic fuels change things dramatically. Here's what I mean. When you start up a boiler, the steam's going to form. We're going to have an air vent down the end here, and they might put that Hoffman number 10 down there. And when the steam starts up, we want this to happen. We want the steam to move through the header, out into the system, and down that line. We want that to happen. Now, there was a system developed by the oil guys in the 1930s that they called master venting. And the original articles that these guys wrote are all on heatinghelp.com. If you want to read them, just drop me a line at dan@heatinghelp.com, and I'll point you right at them. But it was the oil guys complaining about how in the days of coal, they would pipe the coal boiler in a certain way. The coal boiler would often be near the street because that's where the coal chute was and the coal bin. So that put the boiler on the outside of the house, which is also why chimneys are on the outside of the house. It just became a traditional thing to do. Now, since they were firing coal, which would come on and run for 8 hours or 10 hours continuously, they were able to run perimeter mains around the whole building. So they'd come off the coal boiler, which was near the wall, and they would run down to the corner with the main and then down to the other corner and just work their way around until they got back to the boiler. So you're basically surrounding the whole building with this main. And off of that, they would run their risers that would go up to the radiators, and the radiators would be positioned under the windows at each room. So that's the way it was done. Now, when you switch over to an automatic fuel, you need to put a thermostat somewhere in that building. And the oil guys would come in and they'd position the thermostat somewhere in the middle of the building, figuring that was a good neutral spot. Well, the problem was the perimeter main that was designed to run with a coal fire would get hot about halfway around and the thermostat would be satisfied. So now they had heat on one side of the building and no heat on the other side of the building. So that the oil guys were faced with this challenge, and they realized that if they were putting in a new steam system, they would now, for the first time, rather than use this perimeter main that went around the whole building, they would come off the header with multiple mains, and they would go, left side with one, right side with the other, tie them together on the other side and bring them back through a wet return, or they would go even more runouts. So when you're on an old job, if you see that perimeter main, know that you're looking at a job that was piped to fire coal. And if you see a manifold coming off the header with multiple takeoffs going in opposite directions, that was a job that was piped to fire an automatic fuel. So in their articles back in the 30s, they talked about dealing with the distribution of these piped for coal jobs by using master venting. And what they did was what you see here in this picture. They put a big main vent like that Hoffman number 10 at the end. Now you could apply this same kind of logic nowadays by doing this. Walk down the end of the main. Get out of the boiler room. Don't be a flamehead. Get out of the boiler room, wander through the building, and when you get down the end of the main, you're looking for a vent. Ask yourself this question: if I were air, could I get out? And you're looking for a main vent somewhere down the end of the line. I guarantee you, when you get down the end of the line, you're either going to find a vent that's broken and it's stuck closed, or you're going to find where a vent used to be and there's a pipe plug in its place. Or you're going to find a little radiator air vent drilled into the side of the main, which is crazy because it can't vent much air other than what's in a radiator. So you got to look at that. And when you find that hole that's now plugged, I want you to take the plug out of the hole with the system off, and then go back there and start the boiler. Put your hand on the header. As soon as the header gets hot, That's telling you that steam is now leaving. Okay, now when the header gets hot, run down to the end. You're going to be running a stopwatch now. So when this gets hot, start the stopwatch, run down to the end, and see how long it takes for the steam to come out of the hole. That is the venting rate of the hole on the main. Does that make sense? Good. So now what you want to do is select the proper size vent that can vent that much air in that amount of time as if it wasn't there. So in other words, you're picking a vent that has the capacity to vent of the open hole. And if you want the steam to move even faster, you can add holes and vents. So this is master venting. So the steam will now favor the main and not go up the risers till it reaches the end of the main. So let's take this a step further here. Jerry Gill and Steve Pajak are two very, very sharp contractors who work out of Cleveland, Ohio, where there's a lot of steam heat. And Jerry and Steve have been friends of mine for years and years, and they put together this balancing steam systems using a venting capacity chart, which you can look at for free on heatinghelp.com. And you could use all this. And they did this in 2005, and they've been updating it ever since. Now, Jerry and Steve knew about master venting, and they were out there using the vent valve venting rates that the manufacturers of the venting rates published. But those were published back in the 1930s and 40s. And Jerry and Steve began to suspect that they weren't that accurate. So they went out and they got everybody's main vents, the current ones, and they also had antique air vents. They went out and tested every air vent, and not only air vents, but also steam traps, because before a trap can trap steam, it has to vent air. They tested everybody's air vents, and they did this using a Dwyer meter, which could measure the venting of air through a very tiny orifice at just 1, 2, or 3 ounces of pressure differential. And they published their findings in this, and it was eye-opening because none of the manufacturer's literature held true. It was all off, and it was off by a lot. And they realized this by trying to balance systems, and they weren't getting anywhere. So they came out with this, and this changed everything. So what Jerry and Steve did was they looked, for instance, at the venting capacity of main vents, and this showed you all of that. And you could just see these magnificent differences. And then they said, okay, let's make more main vents. So they began to talk about this, and a lot of it got passed on through heatinghelp.com. And this was one job that was done not by Jerry and Steve, but by a fellow we call Steamhead, who works out of Baltimore. And Steamhead is Frank Wilsey, that's his name. And Frank went out there, and he went into a 100-year-old apartment building that had problems for 100 years and really, really high fuel bills. And Frank went in there and master vented it. And Frank added 25 main vents and lowered a $35,000 fuel bill by 32%. He did this with vents. Now, that's what I call low-hanging fruit. There's no reason to rip out the steam system if you want to be more efficient. There's no reason to redo the whole building. You just need to tweak. You just need to know what it is you're doing, and you can get results that are just like that. 32% savings on a $35,000 annual fuel bill with 25 main vents. This can be done. In New York City, there's a friend of mine named Paul Shea who runs a company called It's a Real Good Plumber. And Paul goes out into these older buildings in Lower Manhattan and does the same thing with master venting. Look at the amount of air vents we're talking about here to get the system to heat very quickly. Look at this. And they get incredible results by doing this. System operates on several ounces of pressure. We're talking big buildings here. Several ounces of pressure, no hammering, no noise, even heating, low fuel bills. It's all being done with venting and through this master venting approach. So we're going to do this. We're going to get the steam to go down to the end. And the way we do that is we measure the air that's in that pipe and we put in an appropriately sized vent. The next thing we want to do is look at the risers, because that's our next challenge. So we're going to vent the tops of each of these risers. And then we're going to measure the air that's in this pipe going up. I'm going to size that vent to handle only that air, this vent to handle only this air, and so on. And then we look at the radiator air vent, and we say, okay, that only has to handle the air that's going in this pipe and the radiator itself. So many times you'll hear people say, well, if the radiator is far from the boiler, you have to heat it, or you have to vent it quickly, and if it's near the boiler, you have to vent it slowly. Well, that's not true. In fact, in the 1930s, the oil guys wrote literature where they said, that's just not so. Now, the reason this master venting came to be, because if the radiator is far from the boiler and it happens to be a small radiator, that's because it's in a small room. If it's near the boiler and it's a big radiator, it's in a big room. So a big radiator has got more air in it than a small radiator, and if our goal is to get every radiator in the whole building to heat at the same time, obviously we have to vent the big radiator faster than the small radiator because the big radiator contains more air. So by master venting, since we put in vents that will favor the steam to go up the main vents, the main risers and down to the end of the main, when steam comes up, it doesn't go right to the radiators. It blasts down to here. It goes up the risers, and I'm talking about speeds that are crazy fast. I did a seminar in New York recently, and a guy was there who was the guy that was in charge of the re-engineering of the heating system in the Empire State Building. And I was talking about the Empire State Building and how it runs on low pressure and such, and he came up to me afterwards, and he said, Dan, I got to tell you, I'm that guy, and I was delighted to meet him. And he said, we were trying to figure out how fast steam will move if we allow it. He says, and a lot of the stuff we had gotten out of your book, The Lost Art of Steam Heating, when we were doing this, and he says above the main observation area, there's a smaller observation area at the Empire State Building, and above that there's a room with a radiator. He says nobody goes up there except the people who work there. He says that's on a riser. He says I had them close the valve in the basement, and I stood up there in that room, and I phoned down to them, and I said, open the valve. He says, the heat was at that radiator in moments. He says, you are so right. This stuff wants to move at the speed of sound. He says, the only thing standing in its way is the air. So there's a real story for you, and this is stuff that anybody can do if you just look at that booklet, which is on our website, and it's free. And you go out and you get yourself a pipe caliber, which you can also get on our website to see how much air is in the pipe. And then you look at this chart, which is also in that booklet, which is on the website, which is free, Jerry and Steve's booklet. You want to know how much air is in a 2-inch pipe? Well, there's that much per linear foot. That many cubic feet per linear foot. How about in a radiator? Well, you figure out what kind of radiator you have. If it's a cast iron column radiator, the classic steam ones, well, there's 0.025 cubic feet per square foot of EDR. So if you know the EDR rating, you know how much air is in there. Knowing this, you could do anything. You could do stuff other people say is impossible. So we vent by volume, not by the location. We don't vent fast vent fast because it's far, it's slow because it's near the boiler. You vent by volume, not by location. This stuff works, my friend. And then Jerry so beautifully said, before a trap can trap steam, it must vent air. So the steam goes out at the end. It's climbing up the ladder. The radiators are the rungs on that ladder. These red dots are the steam traps. It's pushing the air through here into the return, and it's got a vent over here. So Jerry and Steve did something that nobody in this industry had ever done before. They tested the venting rates of steam traps using their Dwyer meter. And what they found was pretty interesting. There's a lot of stuff here in that booklet. For instance, the Hoffman 17C with the half-inch capsule that comes with it has a venting rate of 0.53. Now, if you exchange that with a Barnes & Jones cage unit, the replacement part, the venting rate goes up by 2.5 times. So this has meaning when you're changing traps in a riser that goes up through, say, the bedrooms of an apartment building, 1A, 2A, 3A, and so on. If you change some of the traps and repair them with certain parts and other traps and use other parts, your venting rate is going to be way different and your distribution is going to be way different. So knowledge is power, and the more you know about this, the more problems you could solve. Water hammer we've talked about quite a bit today, but this is what you have, just graphically showing. You got water laying in a pipe when it shouldn't be, and you've got steam moving across the top at gale force winds, and it's going to pick up that water, and a slug's going to form, and that slug's going to get propelled down the end of the main where it's going to hit something and make a turn, and it's going to hit it with enough violence that it can actually rip the pipe right out of the fitting. And that happens. So we want to avoid water hammer. We also want to avoid water hammer by not being knuckleheads. For instance, this fella piped this one-pipe steam radiator with this in it, figuring that water will somehow be able to climb back over this hump and drain down the pipe. So I hope you're laughing right now. I can't see your face, but I'm imagining you're laughing. I like that. Let's laugh some more. This is a one-pipe steam radiator. We've got the inlet in the top. There's a vent down under here. And we expect condensate now to climb back out of the radiator and down the pipe. Looks good, though, doesn't it? And he put a drip pan in there to collect the condensate. And there is the shoe of the person that did this. So way to go. Way to go, fella. Now this was on a job in Brooklyn. This is a steam job with tremendous water hammer, but the contractor decided that he was going to screw an external tank that you would use in a hot water heating system as its compression tank into the side of the steam riser going up to the header, figuring it would act as some kind of a plumber's shock absorber. So that didn't work either, but way to go. This is, I have to show you this because you wouldn't believe this if I just told you about it. They add an addition to the back of a house in Long Island. And they build out over the back stoop, and they put in this crawl space, and they add a steam radiator because it's a steam heated building, this house, and they run the main out through an uninsulated main out through the cold crawl space, and the air vent, of course, begins to squirt water all over the ceiling when they start it up. So the plumber comes back and he solves this by doing this. He installs a pop bottle over the air vent's inside there. And then we're going to drill a hole in the floor. We're going to go down to the crawl space with this garden hose. So let's go in the crawl space. Okay, here the radiator's over here, back here. You can't see it, but here comes the hose. And we're going to secure it in place with a piece of lumber and some twine. So this is going across the uninsulated crawl space, and it's going to go the other way. So let's turn around and face the opposite direction. Here we go. Okay, here it comes. This is the old back stoop, which is now under the crawl space. And we're going to drill a hole through the concrete. There's a drill right there, and it's going to go down into the basement. So now let's go down the basement and see where it goes from there. Okay, here's the other side of the stoop. There's the hole where it came through, and it's just right into the slop sink. And we don't want to waste any of that good Sears hose, so we just leave it all bundled up there. And there you go. So when your only tool is a hammer, every problem looks like a nail. So there you go. That's your competition. Also, your competition. This was posted on the website by a contractor who said he walked out and he saw this house that had a steam main vent sticking out of the side of the house doing that in the winter. And he knocked on the fellow's door and he said, there's steam coming out of that vent that's supposed to be inside the house. And the guy says, oh, yeah, it does that all the time. So thanks. There you go. Now, let's get the water back into the boiler. There's a lot of different ways we can do this. Let's talk about getting it back. First, we got that over popular A dimension, the 28 inches, simple as can be. The gravity, the weight of the water in the pipe is going to make the water go back into the boiler, but you got to make sure that you have at least 28 inches, preferably more, if you can, between the center of the gauge glass and the bottom of that lowest horizontal steam carrying pipe. That's why boilers wind up in pits. This guy took the boiler out of the pit, got severe water hammer, called me up, went and took a look. I said, why'd you take the boiler out of the pit? He says, I couldn't figure out why it was down there. He says, what am I supposed to do now? So I said, well, I guess you either have to put the boiler back in the pit or you have to invest in a boiler feed pump and some steam traps because you don't have enough A dimension. And he says, who's supposed to pay for that? And I said, you are. And he said, why should I pay for it? I didn't know. I said, well, that's why you should pay for it, because you didn't know. And he says, well, how do you figure that? I said, well, that's called tuition. Now, here are motorized valves, which I really despise because they cause all kinds of problems. Motorized valves are often sold to churches and places like that where there's not a lot of money and there's a lot of steam and there's a lot of problems. And the idea is, well, why heat the whole place when you could heat just part of it? So here's the challenge with the motorized valves. First of all, we got an A dimension over here, which is 28 inches in total. There's the main vent at the end. And there's 2 pounds of steam pressure in the boiler. And let's say this boiler is 1 million BTUs. So all this piping on both sides is sized to accommodate and accept 1 million BTUs worth of steam volume at a pressure drop of about 1 ounce of loss for every 100 feet of travel. So that's what everything wide open before the motorized valves were added, which they were never there in the beginning. So now we got a motorized valve and somebody comes along and closes that. So ask yourself the question, when somebody closes that, who changes the size of the boiler from 1 million BTUs to 1/2 million BTUs, since that's all we need? And the answer is nobody does. So the boiler continues to produce 1 million BTUs, and we're now trying to put 10 pounds in a 5-pound bag. And since it's a gas, you could do that. But you can't do that at a pressure drop of 1 ounce of loss for every 100 feet of travel. What suffers is the pressure drop. It gets tremendously higher. So instead of having that leftover steam pressure out the end, you're going to have less pressure and you're going to get water hammer over here when the boiler is running on the one zone. Meanwhile, over here, you got 0 psi over here because the motorized valve is closed. So the 0 psi, and this is open to the atmosphere. That's a main vent. 2 pounds of pressure in the boiler, no pressure in this pipe. So I would imagine that the pressure in the boiler is going to just shove the water up this line, completely fill the main when that motorized valve is closed. It's going to flood it right back to the valve, right? Okay, so now imagine what happens when that valve opens and Mr. Steam meets Mr. Water in this horizontal pipe. Right. You're going to get water hammer that's going to lift the church off its foundation and hammer like crazy, and it's going to take all that water back into the boiler, which has been getting replenished by an automatic water feeder, and suddenly your boiler's flooded right up to the top of the header. Somebody has to go downstairs because now you can't make steam and drain the boiler back to here, and they'll do this every single day of the winter, spending money on water, on chemicals, on damaged sections. I mean, it never ends. Because keep in mind over here, once this valve closes, this becomes a B dimension, and you need 28 or 30 inches of vertical height for every PSI pressure. We don't have it. Condensate pump is a great way to return water to the boiler if the boiler doesn't mind getting it. So we've got a float that goes up and turns the pump on, and the water comes out, and the float goes down, and the pump goes off. So it is not asking the boiler whether it needs this, it's just sending it on its way. So in some cases, the boiler feed pump is a better choice because this does not have the float inside of it. It's got the pump here. It's got an oversized receiver to accommodate all the water that's coming back. That's not going to go back into the boiler. It waits here in reserve. And on the boiler, we've got a float-operated pump controller. Here's an older one that's operating on a mercury switch, which we're not allowed to use anymore for good reason. And nowadays, you probably see probe type with this be pump on, pump off, 2 probes like this. That's more likely. And now if we have a motorized valve on here, consider this. Now there's your condensate pump, or your pump controller in this case is operating a boiler feed pump. I apologize. And there's 2 pounds of pressure in the boiler. And you got zone valves over here, the motorized valves, and they both close. So now they're both shut. Think about what happens next. There's steam in the boiler, there's steam in this pipe, and there's steam in these pipes here. So as soon as the motorized valve shut and the boiler burner shuts off, all of this is going to condense, and you're going to get a very deep vacuum inside the boiler, inside the header, and in the pipes up to the motorized valves. As soon as you get the vacuum forming there, air is going to enter the vent line of the condensate pump, push the water that's in the boiler feed pump, push the water in the boiler feed pump through the check valve and flood the boiler. And this happens so fast that if you're watching the gauge glass at the moment it happens, you'll swear somebody opened a fire hose to fill that boiler. The water will just rush right to the top of the gauge glass, continue to flood into the boiler, and go right up into the header. Very common problem, and the solution is to get a vacuum breaker somewhere here above the water line to break the vacuum that's being formed when these things close down. Again, it's common sense, but it's often missed. It's often missed with the vacuum pumps as well. And I told you about these earlier and how they work in bigger buildings, but let's say we're putting in a new boiler and it's smaller than the old boiler, so we want to add to the mix a boiler feed pump. So in this case, we've got the vacuum pump, which comes on with the burner to pull a vacuum through all these pipes, and the vacuum gets pulled right back to the surface of the water. So we got vacuum in the boiler. The condensate comes, the vacuum pump dumps the returning condensate into the boiler feed pump, which is vented to the atmosphere, and the boiler feed pump pumps it into the boiler, but only when the pump controller calls for it. But consider this for a minute. The vacuum pump is creating a vacuum inside the boiler, above the water line. The boiler feed pump is vented to the atmosphere. So as soon as this begins to go to vacuum, the atmospheric pressure is going to take the water in the boiler feed pump, shove it through the check valve, and flood the boiler. And again, it's a very common problem. And the way around that is on this application where you have to have a vacuum pump and a boiler feed pump, don't use a check valve here. Instead, use a motorized valve on that feed line. So then you take your pump controller and you wire it to the motorized valve, and the motorized valve has an end switch that starts and stops the boiler feed pump. And that's the way around that problem of the flooding when you've got a boiler feed pump combined with a vacuum pump. Okay? Good. You're looking good. I'm glad you're getting all this. All right, back to the days of vapor heating. I want to tell you about the boiler return trap because there are still many of them out there. A lot of people get confused when they look at them because they don't know what it is. And also it's named trap, which it's not. So it's not an aptly named device. It's actually a mechanical condensate pump. They come in different shapes and sizes, but they all did the same thing. So let's look at one. This one was made by Hoffman. It's here. And over here we've got this with this return line coming back from the radiators. So there's a steam line coming in here and an exhaust line that's coming over the top. So this is the boiler return trap, and this is the receiver and air vent. Now, this is going out to the radiators, the steam line. This is coming back from the radiators. So the condensate is coming out of radiators that have steam traps on them, thermostatic traps. The condensate bypasses this line and goes back into the boiler. This exhaust line is equalizing the end of the dry return, coming back from the radiators, into the boiler return trap. So hang on a minute. This is the air vent for the whole building. This little thing here. Very, very small, very easy to miss, but essential. Looks like that. It's a 3/4 inch tapping, and if you remove the cap, what you see in there is a ball. And that ball was designed to produce vacuum in the days when we were burning coal. So the steam, as it pushed the air ahead of itself, would make the ball pop up, the ball would seat, and then when the steam condensed, you'd get vacuum. So unless you're burning coal, I would remove that ball. So I would find this, get a needle nose pliers, just unscrew the top, take the bowl out, put the cap back on, put the bowl in your pocket, add it to your collection. Now it can't make vacuum. So the receiver and the air vent on the inside looks like this. What we have here is just a float valve, like a ball cock in a toilet. Your vent screws into here, and this is down there. It's normally down. Venting is going to go through there, coming down here. And the only time this would go up would be if water somehow managed to come up this line, because we don't want this to spill. So that's there to prevent spillage. And the only way water could come up this line would be if somebody in the coal-fired days left the ash pit door open and the fire flared up and you had too much heat, too much pressure, water would back out of the boiler. So if this is there and it's fine, leave it alone. Don't change any of this stuff. This guy over here, I'm going to explain to you in a minute, but the way to know whether it's working is when it's running, you feel the steam line, it should be hot. This line over here to the touch should be cold. If this line is hot, something's wrong. It should not be steam in this line. So here's what we just looked at. There's the boiler return trap. This is that exhaust, the receiver of air vent, right in the top. So the steam is going out. Here's the near boiler piping. It's going out to the radiators. It's coming back here from the radiators. And notice how we have 19 inches from the end of the main down to the water line. Now 19 inches represents about a ½ pound of static weight. So that means that as long as the boiler is operating at 8 ounces of pressure or less, and that's what we call vapor heating, when it's 8 ounces of pressure or less, there'll be enough weight in this line to overcome that check valve. It can open that check valve and open this check valve over here, this inboard, the inboard and the outboard check valve, these two here. It can do that because this is equalized to that. So this is a U-tube right here. So the 19 inches of weight will open this check valve, open that check valve, put the water in the boiler, as long as there's at least or not more than 8 ounces of pressure in the boiler, 1/2 pound. But if the pressure should go above 1/2 pound, what happens is the boiler pressure shoves back against this check valve, so it closes it. Now over here, we suddenly have enough weight to open this check valve, but we can't get the inboard check valve open because of the excessive pressure of the boiler keeping it closed. So the water just shrugs its shoulders and it says, okay, well, I'll just go up this line over here and I'll enter the boiler return trap. Now, once it gets in there, what it's going to find is this. There's a float, and the float is operating two valves. It's mechanical. One is a steam line, which is normally closed. The other is that exhaust line, which is normally open. So the float comes in here. The water comes in here, raises the float, and when it gets to a certain point, these valves go clip-clop, they reverse action. The steam line opens, the exhaust line closes. Suddenly, steam is in this line. It pushes down on the water, shoves it down, shutting that check valve, opening that check valve, and putting the water back in the boiler. Now, as the water level goes down inside the trap, the float goes down with it, And once again, clip clop, steam side shuts, return side opens, the exhaust line, and you're ready for another cycle. So this thing will cycle up and down and up and down. So it's not a steam trap, it's a mechanical condensate pump. They are remarkably long-lived, and they came in all different shapes and sizes. This is one made by Dunham Bush. There's the boiler return trap, there's the vent, and there's the 2 check valves. And when you look at this thing close up, cut it open, you can see there's the steam and the exhaust line, and there's the float. That's all that's in there. And I have a contractor, actually a wholesaler friend in Pennsylvania, who figured out that if one of these things, fails because the valves are not seating properly, or the linkage breaks, rather than replace it with a boiler feed pump and steam traps and a whole lot of expense, what he does is he has the contractor rip the guts out of it, and then he takes a probe type low water cutoff and he sticks it in any one of the holes. I mean, they all had plenty of tappings in them, and he gets a solenoid valve that would be normally closed, a small solenoid valve that he would put on the steam line going to this, and another solenoid valve that would be normally open, and he puts that on the exhaust line. And he wires those through a switching relay to the low water cutoff. So when the water comes up, and now it's just using this body as a place to gather water, when it touches the probe, it makes the electrical connection through the switching relay and reverses the connections of the signal to the 2 solenoid valves. So the steam line opens, the exhaust line closes, and the whole thing works. So you get another 250,000 miles out of it for a couple of $100. So don't take it out if you don't have to. And all day long we're talking about pressure, right? Pressure's important, but maybe not in the way you think. 2 pounds of pressure, that's all you need to heat that bad boy. It's also in a vacuum system, so we do have some negative pressure on the return. But 2 pounds of pressure, that'll do it. And that's because pressure on the gauge on a low pressure boiler doesn't go above 15 pounds. In the old days, they used gauges like this because it would also go into vacuum if we were firing coal. But it's not the pressure that heats the building. We have to figure out what pressure we need. And for that, we look at the pressure troll. And, we've looked at these a bunch of times today already. It's got a cut-in setting. It starts at 1/2 psi. And when I started out in this business, I was trying to figure out, what should that be set for? So I would go to these little local trade shows. I worked for a manufacturer's rep at the time. We didn't sell pressure trolls, and we didn't sell boilers. But I'd say to the boiler guys, how do you set that? And they'd say, well, you set it for whatever it needs, which wasn't really a good answer. So I'd ask more people. They'd tell me the same thing. One guy says, go ask the Honeywell guy. And I went over, he had a booth, and I asked the Honeywell guy, and he says, I'll send you the instructions before the internet. So he sends me the instructions. It comes in the mail, and it's going to explain everything. And the instructions say, set the cut-in scale to the desired pressure. And I said, oofa. Right? This is whatever you desire. So that was as clear as mud. Thank you very much. But when you open it up, you'll see this little wheel here, and that says differential, DIFF. So the cut-in plus the differential equals the cut-out pressure. So if you set this to cut in at 0.5, half pound of pressure, with a 1 pound differential, it'll operate between cut in at a half, cut out at 1.5 pounds. So Honeywell in their instructions told me how to set the differential wheel for heating system, and they said that I should set it to the number of pounds that the pressure differential should rise above the cut-in setting. So the cut-in is whatever I desire, and the cut-out is whatever it should be. Thank you very much for that useful bit of information. And it wasn't until after that I realized that it's not the pressure that's heating the building. This is when I did other research, read lots and lots of books in full, and learned about the national poison, which was vitiated air. I learned about the great influenza, the Spanish flu. I learned about the Carbon Club and how they decided 2 psi is all we need on December 19th, 1898. And I realized that it's not the pressure that heats the building. It's the latent heat that's in the steam. So, for instance, if we wanted to change a pound of water, which is about a pint, from liquid to steam, if we started at 32-degree liquid water, not ice, and we got a 212-degree liquid water, not steam, because water can be in either state at 212 degrees or at 32. It's good that way. Well, we would have to add 180 BTUs, because 1 BTU will raise 1 pound of water 1 degree Fahrenheit. So to get from 32 to 212, that's 180. But now we don't have, that's not steam. That's just really hot water, 212 degree water. To get steam, it would be nice if we could like throw one more BTU into the pot, one toke over the line, and suddenly you got steam. But then a watch pot never boils would not be true. No. To get that pound of water to turn state, to get those little molecules excited enough that they leap off the surface of that water, we have to add a magnificent 970 BTUs per pound. And it's still only at 212 degrees. It's at 0 psi. Now, that's the heat that's going to heat the building. Right there. That's called sensible heat. Because we could sense it. This is called sensible heat. I'm sorry. We could sense this with a thermometer. This is called latent heat because we can't sense it with a thermometer. It's just there. You can't see it though. At this point, all we need to have is enough pressure to move through pipes, the steam through pipes, which was sized since 1899 at a pressure drop of 1 ounce of loss for every 100 feet of travel. So this is why steam systems will work at 2 psi if you'll only get the air out of its way. And that has nothing to do with pressure trolls. That has to do with air vents and master venting, and steam traps that work, and pipes that are insulated, and near boiler piping that's correct, and all this stuff that we've been talking about for hours. Crank it down. You don't need pressure to heat a building. If you crank it up, you're going to lose every single time. Steam traps do trap steam. But first they have to vent air. So here's a beautiful old Warren Webster trap, which shows the workings wonderfully, and that's connected to the radiator. The air gets pushed through there first, and out the bottom it gets vented somewhere downstream. Over here you've got this bellows that's filled with a mixture of alcohol and water and sealed under vacuum, designed to scrunch itself up, and when the steam comes along it's going to heat that alcohol and water mixture and cause it to expand, pushing that pin down into that seat, and the trap is now closed. At this point you need at least a 10-degree drop in temperature from one side of this trap to the other before it'll open. If it's not doing that, the trap's not working. You want to test a trap and you don't have a lot of money for a trap test station? Make one yourself out of an old pasta pot. Just weld something like this on there. You're working in the same building over and over again during the summer. Take the top of the trap off, put it on your pot, see what comes out of it. If steam spews through there, you know you need to replace those parts. If it doesn't, you know the trap is good, put it back where it was. Floating thermostatic trap is both normally closed on the water side and normally open on the thermostat side. So air comes through here, goes past the thermostat, which is normally open, and vents itself somewhere downstream. Steam comes in and shuts that trap. It's the same type of device that you'll find inside of the thermostatic radiator trap. Once that's closed, the steam's rattling around, it's got nowhere to go. It's never a good idea to insulate F&T traps. You want the steam to condense in there. And when it does condense, it turns to water, and the water begins to build up, and the water uses the buoyancy of that float and a lever to pull that pin away from that seat. Now, we want that pin to pull as far away from that seat as possible so you don't have wire drawing, this metal erosion that takes place when you move across there. So we want to size the trap properly. Now, this is the way it's supposed to work. Steam goes down the end, the F&T trap stops it, rises up here, passes through, stops at the traps, air gets vented out of the main vent over here. That's the way it's supposed to be. Now, if I had a 2-inch main that ran out 300 feet, the proper size trap for that 2-inch main would be a 3/4 inch trap. That's based on the amount of condensate that's going to form in that main when it goes from ambient temperature to 215 degrees. A 3/4 inch trap on a 300-foot long main. Now, if you saw a 2-inch main, you're going to see a 2-inch trap on it. That's very common. It's called line sizing of traps. And in the world of heating, I can guarantee you that every single trap that gets sized to the pipe that it's on will be the incorrect trap. And incorrect in that you oversized it. You paid too much for it. Not only do you pay too much for it, but it's going to fail because it's oversized. And most of the time, it's just going to be barely lifting the pin away from the seat. That's going to cause metal erosion, and the trap's dead. So don't get sucked into that. This is the way traps are supposed to work. They're supposed to trap steam. But let's consider for a minute, if this one trap over here on the first floor, this one guy, his trap fails. Now, when it fails, there's no obituary in the newspaper. It doesn't shout, it doesn't grab its chest, it doesn't fall to the ground. It just dies. And often it dies in the open position, because that's the position that will cause the most grief. So let's see what happens now. Steam comes up, goes down the end of the main, and starts to climb the ladder But since that trap's failed, it crosses into the return. And, oh, look, now it's in the return. Now it's in the return downstream of the trap. Oh, it just shut the air vent here. So both lines are filled with steam, and everybody above this guy has no heat. Now, this is one of those things that's true of life. The guy with the bad trap will always have heat. He will never call you. It's everybody above him. They'll have no heat. So you won't go to this guy, you'll go to these people. And when you go up there, you're going to find, everything seems okay, except that the radiator is not heating. So you're going to be tempted to pop the top of the trap. And when you do that, a big rush of air is going to come out, and the radiator is going to get hot. And then you're going to say to yourself, oh, obviously it's not letting the air out. So you're going to do what is in the world of steam heating, the stupidest thing possible. You're going to put a one-pipe steam air vent on a two-pipe steam radiator. And I say it's the stupidest thing because the air is going to come out of the radiator, and the radiator is going to get hot. And when the trap, which is closed, gets flooded with the condensate that's trying to get out, it's going to open, and the steam's going to come up the return line backwards, looking for that air vent, and it's going to hit the trap backwards and destroy it. So by putting the air vents on your radiators, you're going to wreck all the radiator traps in the building. And once the radiator traps are failed, you've got steam in both the supply and the return. There's no distribution. The boiler's going off on low water. You're spending money on chemicals and on water. Nobody's got heat, and there's water squirting out of the air vents, and the boiler's flooding because there's an automatic feeder that's replenishing the water they can't get back from the radiators. And all of this is being caused by somebody adding an air vent to a two-pipe radiator. So it truly is the stupidest thing, because rule number one in all of steam heating states that when you do something stupid, you'll always be rewarded in a small way. You wanted that radiator to get hot? You got it hot. But because you were so monumentally stupid, the whole system's going to fall apart now. It's just in the cards. So don't get sucked into that. Also note, too, that if you see these old-style radiator valves that had little pins on them that you see here, and they had these markings on the top. They were these cast into the top markings. And what you need to know is that every one of those markings represents 10 square feet of EDR. Because this radiator valve has an orifice built into it that's variable. So depending on how much you opened it, it would be able to allow in only as much steam as the radiator would condense. And the installer, back in the old days, would peg the radiator at that point. And because he did this radiator is not going to have a trap. So you'll see this type of an inlet valve, and you won't see a radiator trap on that radiator. So what you got to be careful about, though, is if you replace this old-style radiator valve on the supply side with a modern radiator valve, that's not going to have an orifice in it, and now suddenly you better have a steam trap on there. Otherwise, you're going to send steam full bore through the radiator into the return and mess up the whole building. So one way around having to use a radiator trap would be to open this union connection and install an orifice, which is what the old-timers did. Often these were handmade. One of them told me that he used to smoke Prince Albert tobacco because it came in a can, and he had a punch, and he would punch out his own orifices and use a 10-penny nail to drive a hole through the middle of it and be able to heat buildings without using steam traps at all, to just do it with orifices on the supply side. Something to think of. So there you have it. Thanks for spending time with me. If you got any questions, you come down to here to heatinghelp.com. There's a tremendous amount of information there, all for you because we love you. You could just go on the wall, which is our very popular bulletin board, ask a question there, and you'll have answers within seconds. We've got some of the sharpest people in the industry. So thanks so much for taking the time to listen to me. I hope you enjoyed it. It was good being with you. Thank you.